What if I told you that every atom in your body was born in the heart of a star? It's a mind-blowing truth that links us to the universe in ways most of us rarely stop to consider. We are not isolated from the cosmos. Instead, we are intricately woven into its vast and awe-inspiring web, a connection that stretches across time and space. From the explosive birth of stars to the gentle swirl of galaxies, the cosmos is a dynamic, ever-evolving system of forces and events that shape everything we know. As we journey through space, we unlock the mysteries of its formation, observe the life cycle of stars, and probe phenomena that lie beyond the limits of our perception. Our quest extends beyond just understanding our solar system. We seek answers to the existence of planets far beyond our own and whether life exists elsewhere in the vastness of space. As we dive deeper into the heart of these cosmic puzzles, one of the most profound questions that arises is the origin of the universe itself. How did everything come to be? The leading theory that attempts to explain this is known as the Big Bang Theory. It proposes that roughly 13.8 billion years ago, the universe began as an infinitely hot and dense point, a singularity containing all the matter and energy that would ever exist. From this initial speck of unimaginable density, the universe began to expand rapidly, creating space and time as we know them. This expansion marked not just the birth of the universe, but also the birth of time itself. As the universe began to cool, fundamental particles slowly formed. These particles, protons, neutrons, and electrons, collided and combined, ultimately forming the simplest elements, hydrogen and helium. Over millions of years, these elements came together, pulled by the force of gravity, creating the first stars and galaxies. This process is not just a relic of the past, but one that is still unfolding today. We continue to witness the birth of stars within vast nebulae and the dramatic collision of galaxies, a constant reminder that the universe is still very much alive and evolving. However, while the Big Bang Theory holds the lion's share of support in the scientific community, it is not the only idea out there. The steady-state theory, once popular, suggested that new matter is continually created as the universe expands, allowing it to maintain a constant density over time. While this theory eventually lost favor due to mounting evidence supporting the Big Bang, it nevertheless underscores an important aspect of scientific inquiry. The search for answers is never complete. New theories emerge as our understanding deepens, and the nature of the universe's origin is no exception. One such emerging concept involves quantum gravity, an exploration of how the strange laws of quantum mechanics might illuminate the moments just before the Big Bang. Scientists are investigating whether the interplay between gravity and quantum theory could shed new light on the universe's earliest moments, offering clues that could reshape our understanding of its birth. But this quest is far from over. Every day, scientists are pushing the boundaries of technology, observation, and theory to unravel the origins of the cosmos. In this pursuit, new discoveries are continuously refining our knowledge. By examining cosmic background radiation, analyzing the distribution of galaxies, and measuring the abundance of elements from the early universe, researchers are gaining insights into how the universe began and perhaps how it will ultimately end. Each new finding adds another piece to the cosmic puzzle, expanding both our understanding and our imagination. One of the most compelling pieces of evidence supporting the Big Bang Theory is the discovery of cosmic microwave background radiation, or CMB. Discovered in the mid-20th century, this faint, uniform glow is often described as the afterglow of the Big Bang, a remnant of the heat and light emitted during the early universe. The CMB provides a snapshot of the universe about 300,000 years after the Big Bang, when electrons and protons combined to form neutral hydrogen. This allowed light to travel freely for the first time, and that light is what we detect as the cosmic microwave background. The fact that this radiation is consistent across different observations, regardless of where in the universe we look, offers strong support for the Big Bang model. Another critical observation supporting the theory is the redshift of light from distant galaxies. As galaxies move away from us, their light is stretched, shifting toward the red end of the spectrum. The further away a galaxy is, the faster it appears to be receding. This redshift phenomenon directly supports the idea that the universe is still expanding, providing a glimpse into its past. If the universe is expanding now, it stands to reason that at one time, all the matter in the universe was much closer together, an idea that aligns perfectly with the Big Bang theory. As we continue to explore these cosmic wonders, we come to realize just how deeply intertwined our existence is with the universe. Every star, every galaxy, and every phenomenon in the cosmos plays a part in the grand story of creation, and we are a part of that story too. From the atoms in our bodies to the galaxies that fill the night sky, everything around us is connected by forces that stretch back to the very beginning of time. And though we may never fully understand the infinite complexity of the cosmos, the search for answers continues to drive us forward, sparking our curiosity and imagination with every new discovery. The cosmos, vast and mysterious, holds within it a tapestry of intricate processes that have shaped it over billions of years. One of the most profound insights into the origins of the universe comes from the light elements: hydrogen, helium, and lithium. These elements, abundant throughout the cosmos, serve as crucial evidence for the Big Bang theory. This groundbreaking theory proposes that the universe began as an incredibly hot and dense point, exploding into existence billions of years ago. According to the theory, these light elements were formed in the first few minutes following the Big Bang, during a process known as Big Bang nucleosynthesis. The relative abundance of these elements in the universe today closely matches the predictions made by the Big Bang theory, providing a significant confirmation of this cosmic origin story. This alignment serves as one of the key pillars supporting our understanding of the universe's beginnings. Together with other cosmic observations such as the cosmic microwave background, CMB radiation, and redshift, these pieces of evidence form a coherent framework for understanding how the universe evolved from its inception to the vast, complex system we observe today. CMB radiation, often described as the faint afterglow of the Big Bang, holds particular importance. Imagine the universe just moments after the Big Bang, a fiery and chaotic expanse of particles and energy. As the universe expanded and cooled, photons, the particles of light, began to travel freely through space, leaving behind a record of this early state. Today, the CMB fills the universe, acting like a snapshot of the cosmos when it was just about 380,000 years old. Its uniformity, along with slight variations in temperature, offers us critical insights into the early universe's density and structure. These minute temperature fluctuations in the CMB are far from trivial. They reveal essential details about the universe's earliest moments, including how matter clumped together to form the first galaxies and larger cosmic structures. Through the study of these fluctuations, scientists can trace the timeline of cosmic evolution. Each deviation in the CMB reflects a tiny variation in density, a cosmic seed that eventually grew into stars, galaxies, and the vast clusters we see today. In conjunction with the CMB, redshift provides another crucial clue. Redshift refers to the shift of light towards the red end of the spectrum as galaxies move away from us. This phenomenon occurs because the universe itself is expanding, and as galaxies recede, their light stretches, increasing its wavelength. By measuring the extent of redshift, astronomers can determine the distance to distant galaxies and calculate the rate at which the universe is expanding. This relationship between redshift and distance has fundamentally transformed our understanding of the universe, suggesting that it has been in a state of constant expansion since its creation. When combined, CMB radiation and redshift offer profound insights into the universe's infancy. The CMB reveals the conditions of the early universe, while redshift helps us map the universe's structure and evolution. By analyzing how galaxies were distributed over time and how that distribution changed with redshift, scientists can better understand the history of cosmic expansion. Together, these observations form a coherent picture of the universe's dynamic growth, a process that continues to this day. One of the most revolutionary concepts in cosmology is the idea of cosmic inflation. This theory proposes that in the moments immediately following the Big Bang, the universe expanded at an exponential rate. In an incredibly brief period, far less than a second, the universe grew from subatomic scales to nearly the size of a galaxy. This dramatic expansion addresses several key challenges in understanding the structure and uniformity of the universe, particularly the flatness and homogeneity that we observe today. Before cosmic inflation, the universe was an extremely hot and dense state, filled with fundamental particles and intense energy. However, the rapid expansion that followed caused regions that were once in close proximity to become incredibly far apart. This stretching of space-time smoothed out any irregularities, leading to a remarkably uniform universe on large scales. This uniformity is evident in the cosmic microwave background radiation, which, despite slight temperature fluctuations, maintains a consistent pattern across vast distances. This symmetry can be traced back to the thermal equilibrium that existed before inflation, when all regions of the universe were in close contact. One of the most fascinating aspects of cosmic inflation lies in its connection to quantum mechanics. During this rapid expansion, tiny quantum fluctuations, imperceptible at small scales, were stretched to macroscopic sizes, leaving behind the seeds for the formation of galaxies and large-scale structures. These fluctuations became gravitational anomalies, which eventually grew into the stars, galaxies, and clusters that populate the universe today. The study of cosmic inflation, therefore, not only offers insights into the early moments of the universe's birth, but also provides clues about how cosmic processes will continue to influence its evolution. While cosmic inflation helped shape the universe's early development, dark matter and dark energy are crucial to its ongoing expansion and structure. These two mysterious components play pivotal roles in shaping the universe's destiny. Dark matter, which makes up about 25% of the universe's total mass and energy, does not emit light or energy, making it invisible to traditional telescopes. However, its presence is inferred through its gravitational influence on visible matter, such as stars and galaxies. Dark matter acts as a cosmic glue binding galaxies and galaxy clusters together. Without it, the universe would not have the structures we observe today. Galaxies would struggle to form, and existing ones would be at risk of scattering apart. In contrast, dark energy, which accounts for roughly 70% of the universe, is thought to be the driving force behind the accelerated expansion of the cosmos. Discovered through observations of distant supernovae in the late 20th century, dark energy challenges our understanding of gravity. Rather than slowing the universe's expansion, it seems to be pushing galaxies further apart, leading to a constantly expanding universe. This mysterious force operates on a cosmic scale, influencing the future trajectory of the universe. The interplay between dark matter and dark energy is central to understanding the universe's long-term evolution. Dark matter influences the formation of galaxies and large-scale structures, while dark energy dictates how these structures evolve over time. As the universe continues to expand, the density of dark matter remains relatively constant, whereas the effect of dark energy intensifies. This suggests that in the far future, dark energy will dominate the cosmos, ultimately shaping its fate. Despite their elusive nature, both dark matter and dark energy are central to our understanding of the universe's past, present, and future. Scientists are working diligently to unravel their mysteries, seeking to track down the particles that compose dark matter and decipher the true nature of dark energy. By studying these enigmatic forces, researchers hope to illuminate the fundamental processes that govern the cosmos, offering new insights into the universe's structure and its ultimate destiny. The age of the universe, another cornerstone of cosmology, can be estimated using several methods. One key approach involves studying the expansion rate of the universe, known as the Hubble constant. By observing how galaxies move away from us, astronomers can calculate how fast the universe is expanding. This measurement allows scientists to extrapolate backwards in time, estimating when this expansion began and, in turn, determining the age of the universe. In addition to the Hubble constant, scientists also rely on data from the cosmic microwave background radiation. This ancient light, which fills the universe, provides a snapshot of the universe when it was just 300,000 years old. By examining the tiny temperature fluctuations in this radiation, researchers can learn about the composition, expansion, and age of the universe. Current estimates place the universe's age at approximately 13.8 billion years. This estimate has been refined through observations from powerful telescopes like the Hubble Space Telescope and the European Space Agency's Planck satellite. These instruments have measured the cosmic microwave background with unparalleled precision, offering a clearer picture of the universe's evolution over eons. Through these measurements, we not only gain a better understanding of the universe's age, but also glimpse its future. As scientists continue to explore the cosmos, they will continue to refine our understanding of this vast, ever-expanding universe, revealing the processes that have shaped its past and will influence its future. Galaxies, vast systems of stars, gas, dust, and dark matter are among the most fundamental structures in the universe. Their formation and evolution remain some of the most captivating questions in cosmology. According to current scientific models, galaxies formed in the early universe through a process known as hierarchical clustering. This process began after the Big Bang, when hydrogen and helium, the universe's most abundant elements, began to clump together under the force of gravity. Over time, these small clumps merged and grew, forming the galaxies we see today. The formation of galaxies is a dynamic, ongoing process, influenced by both dark matter and the universe's expansion. As we continue to explore the universe, we deepen our understanding of its origins, structure, and the fundamental forces that have shaped it. With each discovery, we are piecing together the grand narrative of the cosmos, unraveling the mysteries that have captivated humanity for millennia. And as we venture further into the unknown, we are reminded of the incredible journey that brought us to where we are today, standing at the edge of the cosmos, seeking to understand our place in this vast and ever-expanding universe. In the early stages of the universe, galaxies were far from the structured, magnificent entities we observe today. They were often irregular in shape, containing mostly primordial gas. As time passed, these galaxies began to evolve, with star formation becoming the driving force behind their transformation. Dense clouds of gas acted as the fuel for this stellar birth, and it was this process of star formation that played a pivotal role in shaping the very structure of these galaxies. Stars formed, lived, and ultimately died, with their remnants contributing to the enrichment of the interstellar medium. The death of stars, through processes like supernova explosions, scattered heavier elements across the galaxy. These elements, which were previously formed in the cores of stars, became the building blocks for new generations of stars, planets, and other cosmic structures. The cycle of star birth and death is ongoing, continually influencing the evolution of galaxies and giving rise to a diverse range of stellar populations. As galaxies continue to grow, they experience various interactions and mergers with neighboring galaxies, which have profound effects on their development. These interactions are not merely superficial. They can fundamentally alter the behavior and structure of a galaxy. When two galaxies collide, for example, the gravitational forces at play can trigger bursts of star formation, creating dense regions of bright, young stars. This process can even reshape the entire structure of a galaxy, leading to new forms and configurations. Far from being static entities, galaxies are dynamic systems that change and evolve over vast stretches of time, stretching across millions and even billions of years. Today, astronomers are increasingly aware of the critical role dark matter plays in galaxy formation and evolution. This mysterious, invisible substance is thought to make up a significant portion of the universe's total mass, yet it cannot be detected directly. Despite its elusive nature, dark matter's influence is undeniable, particularly in the way it shapes the gravitational structure of galaxies. It is the gravitational pull of dark matter that provides the framework within which galaxies form, interact, and evolve. Observations of galaxies suggest that the distribution of dark matter has a profound impact on how galaxies merge, how they interact, and how they evolve into the diverse forms we observe across the universe, from majestic spiral galaxies to colossal elliptical ones. The study of dark matter offers a window into the deeper workings of the universe itself. It provides insights into the ongoing cosmic dance of matter and energy on scales that are nearly beyond comprehension. One of the most fascinating aspects of dark matter is that while we cannot see it directly, its existence is confirmed through its gravitational effects on visible matter. For instance, when scientists observe a galaxy spinning at high speeds, the stars at the galaxy's outer edges should, based on the laws of physics, be flung out into space due to their rapid motion. However, these stars remain bound to the galaxy, held in place by an unseen force. This gravitational pull is attributed to the presence of dark matter, which exerts an invisible force that prevents the stars from being ejected into the cosmos. Estimates suggest that dark matter makes up approximately 27% of the total mass energy content of the universe, a substantial portion compared to ordinary matter, which constitutes only about 5%. The remaining 70% is attributed to another mysterious force known as dark energy. What makes dark matter particularly intriguing is its complete invisibility. It does not emit, absorb, or reflect light, making it completely undetectable through traditional astronomical instruments, such as telescopes. This absence of interaction with light means that astronomers must rely on indirect methods to study dark matter, such as observing its gravitational effects on visible matter. Understanding dark matter is crucial for comprehending the large-scale structure of the universe. Without dark matter, galaxies would not hold together in the manner we observe today. Computer simulations of galaxy formation show that dark matter acts as a gravitational scaffolding, providing the necessary structure for galaxies to form and cluster. It is this distribution of dark matter that has helped shape the vast cosmic web, the large-scale network of galaxies and galaxy clusters that spans the entire universe. This web-like structure is a critical feature of the universe's architecture and holds the key to understanding not only the present state of the universe, but also its evolution over billions of years. In recent years, groundbreaking research initiatives, such as experiments at the Large Hadron Collider and various astronomical surveys, have sought to uncover the nature of dark matter. Scientists are exploring a variety of hypotheses to explain its mysterious properties, including the possibility that dark matter is composed of weakly interacting massive particles, WIMPs. The discovery of dark matter's true nature would have profound implications for our understanding of physics, revealing deeper insights into the fundamental forces that govern the universe. In many ways, the study of dark matter represents one of the most exciting frontiers in modern science, and each new discovery brings us a step closer to unraveling the secrets of the universe itself. At the same time, another cosmic enigma, dark energy, plays a central role in the ongoing expansion of the universe. Dark energy, discovered through observations of distant galaxies, is thought to make up roughly 70% of the total energy content of the cosmos. Unlike ordinary matter, which exerts an attractive force through gravity, dark energy has a repulsive effect, causing the expansion of the universe to accelerate over time. This repulsive force has reshaped our understanding of the universe's fate, and it is one of the key factors driving the cosmos apart. To grasp the full impact of dark energy, we can look back to the early moments of the universe, just after the Big Bang. At that time, gravity dominated, causing the universe to expand more slowly. But as the universe grew, dark energy began to take over, accelerating the expansion. This shift from gravity-dominated to dark energy-dominated expansion marks one of the most significant transitions in the history of the universe. Understanding dark energy and its effects on cosmic evolution remains one of the most pressing challenges in astrophysics today, as it could reveal fundamental truths about the ultimate fate of the universe itself. In the end, the study of galaxies, dark matter, and dark energy offers a profound glimpse into the intricate workings of the cosmos. These forces, though invisible to the naked eye, shape the universe in ways we are only beginning to understand. Each discovery brings us closer to answering some of the most fundamental questions about the nature of reality itself. How did the universe come to be? What drives its expansion? And ultimately, what is the fate of everything we know? These mysteries, though elusive, are at the heart of human curiosity and scientific exploration. And with each passing day, we move a little closer to uncovering the cosmic truths that govern our existence. However, as the cosmos cooled and expanded, the role of dark energy became increasingly important, emerging as a powerful and mysterious force shaping the very structure of the universe. This invisible force behaves almost like an unseen hand, relentlessly pushing the fabric of space itself. Its influence, often compared to a cosmic tug-of-war, is leading to ever greater distances between galaxies, accelerating the expansion of the universe at an unexpected pace. This phenomenon, this surprising acceleration, hints at a deeper, more complex layer of cosmic dynamics that goes far beyond our previous understanding of the universe. It suggests that unseen forces that we are only beginning to grasp, are at play on a scale we cannot yet fully comprehend. One of the most compelling pieces of evidence for the existence of dark energy came from the study of distant supernovae, massive stars that explode in violent bursts of light at the end of their lives. When astronomers turned their gaze toward these supernovae, they made an astonishing discovery. These stellar explosions were dimmer than expected. At first, this finding appeared puzzling. Why were these supernovae faint when they should have been brighter? The answer lay in the fundamental workings of the universe itself. The galaxies that hosted these stars were farther away than predicted by traditional models that had always assumed the universe was slowing under the influence of gravity. Yet the data showed that the galaxies were receding from us faster, not slower, which suggested something else entirely, an acceleration. And that acceleration could only be explained by the pervasive presence of dark energy, an enigmatic force that permeates all of space, pulling galaxies farther apart. Scientists continue to delve deeper into the mysteries surrounding dark energy, trying to untangle its origins and nature. Some theories propose that it be a constant energy density lingering in the vacuum of space, while others speculate that it might be linked to quantum mechanics or even the concept of vacuum energy. Regardless of its true nature, one thing is clear. Dark energy holds the key to understanding the ultimate fate of the universe. As research progresses, it may offer new perspectives on the future of the cosmos, sparking questions and wonder about the vast, mysterious expanse in which we live. Meanwhile, another remarkable discovery has emerged from the depths of space, shaking the very foundations of our understanding: gravitational waves. These are ripples in the fabric of space-time itself, created by some of the universe's most extreme and energetic processes. Gravitational waves travel at the speed of light, distorting the space around them as they pass. They can stretch and compress space, carrying information about the violent events from which they originate. The concept of gravitational waves was first introduced by Albert Einstein in his general theory of relativity over a century ago. However, it wasn't until 2015 that scientists were able to directly detect them, confirming Einstein's predictions and opening up an entirely new way to explore the universe. These waves are typically generated by cataclysmic events involving massive objects, such as the collision of black holes, the merger of neutron stars, or even the explosions of supernovae. When these cosmic catastrophes occur, they send out gravitational waves that convey critical details about the objects and events responsible. For instance, by studying the gravitational waves emitted during the merger of two black holes, astronomers can glean important information about the black holes themselves, their masses, spins, and their distance from Earth. This ability to hear events in space, rather than just seeing them with light, has revolutionized our understanding of the universe. Gravitational waves offer a unique view of phenomena that are hidden from traditional optical telescopes, revealing events that do not emit light or that are obscured by cosmic dust and gas. Gravitational wave astronomy opens up a new frontier in the study of the universe, allowing us to observe the most energetic and invisible processes in space. As our detection methods continue to improve, these waves may even offer insights into the early universe, providing clues about the conditions that existed just moments after the Big Bang. Each new detection brings us one step closer to a deeper understanding of the universe and its fundamental laws, making gravitational waves one of the most exciting areas of cosmic exploration. In this pursuit of knowledge, we are also confronted with one of the universe's most intriguing and mysterious entities: black holes. These celestial objects are formed when massive stars reach the end of their life cycle. Once a star exhausts its nuclear fuel, it can no longer counterbalance the force of gravity. The result is a catastrophic explosion known as a supernova, during which the star's outer layers are ejected into space. What remains at the core, however, collapses under its own immense gravity, compressing all its mass into an infinitesimally small point, a singularity. This collapse leads to the formation of a black hole. The size and mass of the original star determine the type of black hole that forms. If the star is at least 20 times as massive as our Sun, it is likely to end up as a black hole after the supernova. There are also smaller black holes, known as stellar black holes, which form from the collapse of smaller stars. However, there are also supermassive black holes, which can have masses millions or even billions of times greater than that of our Sun. These supermassive black holes are typically found at the centers of galaxies, including our own Milky Way. Their origins remain a mystery, though many scientists speculate that they may have formed through the merging of smaller black holes or from the direct collapse of enormous gas clouds in the early universe. Black holes are not just fascinating objects in their own right. They also play a vital role in the dynamics of galaxies and the universe. Their immense gravitational pull influences the motion of stars and gas in their vicinity. In fact, nearly every large galaxy, including our own, harbors a supermassive black hole at its center. These black holes have a profound impact on the behavior of surrounding material, affecting everything from star formation to the movement of galactic gas clouds. The gravitational waves produced by merging black holes offer astronomers a new way to observe and study these invisible giants. Through the study of these waves, we can learn more about the black holes themselves, how they form, how they interact, and how they shape the evolution of their galaxies. Ultimately, the study of black holes, gravitational waves, and dark energy not only enhances our understanding of the universe, but also forces us to reconsider everything we thought we knew about reality itself. As we continue to probe the deepest corners of space, we are left to ponder the true nature of space, time, and the forces that govern the cosmos. Forces that, despite being invisible to our eyes, shape the very fabric of the universe in ways we are only beginning to understand. Black holes, often perceived as one of the most mysterious and enigmatic phenomena in the cosmos, are essential to our understanding of the laws of physics. They stretch and challenge our most fundamental concepts of space, time, and gravity. By studying black holes, scientists do not only learn about their own formation and life cycles, but also unlock secrets that unravel the very fabric of the universe itself. These cosmic giants offer unparalleled insights into the forces of nature, pushing the boundaries of human knowledge and guiding the exploration of deep space. At the heart of a black hole lies a boundary known as the event horizon. Think of it as a one-way gate to the unknown, marking the point beyond which nothing, not even light, can escape. Once an object crosses this threshold, it is irreversibly drawn into the black hole, sealed off from the rest of the universe. The event horizon becomes an invisible boundary, defining the limits of the observable universe and separating the black hole's internal world from the outer cosmos. It is the last barrier between us and the unfathomable phenomena that reside within. For anyone unfortunate enough to fall into a black hole, the experience would be nothing short of extraordinary and horrifying. A process known as spaghettification would take place. As the object gets closer to the event horizon, it would be stretched vertically by the immense gravitational forces, while simultaneously being compressed sideways. The closer one approaches the event horizon, the stronger the gravitational pull becomes, creating an enormous disparity in the force of gravity acting on different parts of the object. This difference, known as tidal forces, is what causes the body to stretch like spaghetti. What's truly fascinating, however, is how time behaves near a black hole. Due to the effects of Einstein's theory of relativity, time becomes warped. For the person falling into the black hole, the universe outside would appear to speed up as they approach the event horizon. Meanwhile, from an outside observer's perspective, the falling person's motion would slow down and they would seem to freeze at the event horizon. This dramatic distortion of time and space is one of the most mind-boggling aspects of black hole physics, and it challenges everything we know about reality itself. The event horizon is not just a theoretical concept, it's a profound test of the nature of space-time and gravity. Every new discovery about black holes adds another layer of complexity to our understanding of these regions of extreme gravity. As scientists continue to probe the depths of these cosmic mysteries, each breakthrough brings us closer to answering fundamental questions about the nature of the universe. In the search for answers, we also find new questions about the very essence of reality and the limits of what we can comprehend. Detecting and studying black holes from Earth presents a unique challenge. Since black holes don't emit light, traditional observation methods like telescopes are of little use. Instead, scientists rely on indirect evidence. One key method involves studying the behavior of nearby stars and gas. In binary systems where a black hole is paired with a star, the black hole can pull material from its companion. As this material spirals toward the black hole, it heats up to extreme temperatures and emits X-rays. These X-rays can be detected by space-based observatories, offering vital clues about the black hole's presence and properties. Another crucial tool in black hole research is gravitational wave astronomy. When two black holes or other massive objects collide and merge, they create ripples in the fabric of space-time. These ripples, known as gravitational waves, travel across the universe and can be detected by instruments like the Laser Interferometer Gravitational Wave Observatory, LIGO. Since LIGO began operation in 2015, it has made groundbreaking discoveries confirming the existence of black holes and providing detailed information about their mass, spin, and other properties. Moreover, by analyzing the motion of stars within galaxies, astrophysicists can infer the presence of supermassive black holes. For example, the black hole at the center of our own Milky Way galaxy, known as Sagittarius A Lenfrey, was identified through meticulous observation of the orbits of nearby stars. The calculations showed that a massive, invisible object was exerting a gravitational pull on the stars, leading to the conclusion that a supermassive black hole was lurking in the center of our galaxy. Technological advancements are continually enhancing our ability to study these mysterious objects. For instance, the first ever image of a black hole's event horizon was captured in 2019 by the Event Horizon Telescope, EHT. This breakthrough marked a pivotal moment in astrophysics, providing the world with an unprecedented view of the shadow of a black hole and offering insights into its structure. As observational methods continue to improve, so does our understanding of black holes and their role in the universe. The story of the solar system's formation can also be traced back to the processes that govern the cosmos at large. Around 4.5 billion years ago, a massive cloud of gas and dust known as the solar nebula began to collapse under its own gravity. The collapse triggered a chain of events that led to the formation of our sun at the center of the cloud, while cooler outer regions formed the planets, moons, and other objects in our solar system. This primordial cloud was likely enriched by elements from previous generations of stars that had exploded as supernovae. Over time, as the material in the nebula spun and flattened into a rotating disk, the sun ignited through nuclear fusion, giving birth to our star. Meanwhile, particles of dust and ice in the outer regions of the disk began sticking together, gradually forming the planets and their moons. The study of black holes, their event horizons, and their interactions with the surrounding universe is not just an academic pursuit. It's part of a much larger story of how the universe operates. Every discovery brings us closer to understanding not just the black holes themselves, but the forces that shape the cosmos. Through technological advancements, groundbreaking observations, and innovative thinking, scientists are continuously pushing the boundaries of our knowledge, and in doing so, revealing the underlying truths of the universe. The mystery of black holes, along with their profound implications for space-time and gravity, remains one of the greatest intellectual challenges of our time, offering a never-ending source of wonder and discovery. Our solar system presents a fascinating and orderly structure, with the sun at its heart, holding over 99% of the system's total mass. Surrounding the sun, 8 well-defined planets follow their orbits, each with its own unique characteristics. These planets can be divided into 2 main categories: the terrestrial planets and the gas and ice giants. The terrestrial planets, Mercury, Venus, Earth, and Mars, are small, rocky worlds that lie closer to the sun. These planets share a common composition of rock and metal, giving them a dense, solid structure. Their surfaces are rugged, shaped by geological activity over billions of years, marked by towering mountains, deep valleys, and countless craters, testaments to both internal processes and the impacts of celestial bodies. The conditions on these planets can vary drastically, from the blistering heat of Mercury to the freezing cold of Mars. Earth, the third in line, is the only terrestrial planet known to support life, with its combination of liquid water, a breathable atmosphere, and moderate temperatures. On the other side of the solar system lie the gas giants, Jupiter and Saturn, and the ice giants, Uranus and Neptune. These massive planets are positioned farther from the Sun and are fundamentally different from their rocky counterparts. Instead of being made of rock and metal, they are composed primarily of hydrogen, helium, and other gases enveloped in thick atmospheres. Because of this, gas giants lack solid surfaces and are much less dense than the terrestrial planets. Their sheer size is awe-inspiring, with some of these planets stretching thousands of kilometers in diameter. These giants also feature dynamic weather systems with enormous storms and swirling winds. For example, Jupiter is home to the Great Red Spot, a gigantic storm larger than Earth that has been raging for centuries. In addition to their size and composition, gas giants are also distinguished by their complex systems of moons and rings. While terrestrial planets typically have fewer moons, Earth has one and Mars has two small ones, gas giants boast a multitude of moons. Some of these moons, such as Europa and Enceladus, are geologically active, with subsurface oceans that could potentially harbor life. In addition to their moons, gas giants are known for their spectacular ring systems. Saturn's iconic rings are perhaps the most famous, but all gas giants possess some form of rings made of ice, rock, and dust particles that orbit these massive planets in intricate patterns. The atmospheres of the terrestrial planets and gas giants also differ significantly. Terrestrial planets, due to their smaller size and proximity to the Sun, have thinner atmospheres, leading to extreme variations in temperature between day and night. Venus, for instance, has a dense atmosphere that traps heat, making it the hottest planet in the solar system. Gas giants, by contrast, feature thick, swirling atmospheres filled with clouds and violent storms. The gravity of these massive planets holds their gaseous envelopes firmly in place, preventing them from escaping into space. This stark contrast between the two types of planets, terrestrial and gas giant, affects not only their physical properties, but also their potential for supporting life. While Earth is the only known planet in our solar system capable of hosting life, the study of gas giants and their moons opens intriguing possibilities for the discovery of life beyond our world. Beyond the planets, our solar system extends into the Kuiper Belt and the Oort cloud. The Kuiper Belt is a vast region that lies beyond Neptune, home to numerous icy bodies and dwarf planets, including Pluto. These objects are remnants from the early solar system, relics from a time when the Sun and planets were just beginning to take shape. The Kuiper Belt marks the boundary between the planets and the more distant, icy objects that inhabit the outer reaches of the solar system. Far beyond the Kuiper Belt lies the Oort cloud, a theoretical shell of icy objects that forms the outermost boundary of the solar system. Though never directly observed, scientists believe that the Oort cloud holds a vast collection of icy bodies and comets, some of which may one day travel into the inner solar system. The Oort cloud represents the farthest frontier of the Sun's gravitational influence, a region that remains largely unexplored but holds potential clues about the origins of our solar system. Asteroids and comets, too, play a crucial role in our understanding of the solar system. These celestial bodies are like time capsules, preserving the chemical signatures of the solar system's infancy, offering scientists a window into the early stages of planetary formation. The asteroid belt, located between Mars and Jupiter, is populated by rocky and metallic objects that provide insight into the conditions of the inner solar system, where the terrestrial planets were born. Comets, on the other hand, originate from the colder regions of the solar system, often far beyond Neptune. Composed primarily of ice, dust, and organic compounds, comets are known for their dramatic tails, which form when they approach the Sun. As the heat from the Sun causes the volatile compounds within the comets to vaporize, they create a spectacular display of gas and dust trailing behind them. These icy visitors are believed to hold important clues about the building blocks of life, and many scientists speculate that comets may have played a role in delivering water and organic molecules to early Earth. Together, asteroids and comets offer critical insights into the solar system's formation, helping scientists piece together the story of how our cosmic neighborhood came to be. Through their study, we can better understand the processes that led to the creation of planets and the conditions that may have allowed life to emerge on Earth. Each icy fragment, each rocky body, holds a story that stretches back billions of years, offering a glimpse into the early solar system and the forces that shaped it. As we continue to explore our solar system, we uncover more about its vast complexity and the diverse worlds that make it up. From the solid surfaces of the terrestrial planets to the swirling storms of the gas giants, and from the icy comets at the fringes of the Oort cloud to the dusty rings of Saturn, the solar system remains an endlessly captivating and dynamic region of space. Each discovery brings us closer to understanding the intricate dance of our cosmic backyard, revealing the forces that govern its structure and the mysteries that still await our exploration. Throughout Earth's history, the impacts of asteroids and comets have profoundly shaped our planet's geology and atmosphere. These celestial bodies, often seen as distant travelers in the cosmos, have played crucial roles in the formation of Earth as we know it today. One of the most significant events in this cosmic drama occurred approximately 66 million years ago, when a colossal asteroid collided with our planet. This catastrophic event is widely believed to have contributed to the mass extinction that wiped out the dinosaurs, forever altering the course of life on Earth. The aftermath of this event not only marked a dramatic shift in biodiversity, but also provided a stark illustration of the immense power that these space objects wield over planetary systems. The idea that a single asteroid could reshape the planet's evolutionary trajectory underscores just how intertwined Earth's fate is with the larger cosmos. It serves as a reminder of the vulnerabilities and resilience of life, with the ability of a celestial body to forever alter life on Earth being both awe-inspiring and terrifying. As our curiosity grows, so does our determination to understand the role that asteroids and comets play in the universe. Modern space missions targeting these ancient space travelers aim to provide a deeper understanding of their nature. Notable missions such as NASA's OSIRIS-REx and the European Space Agency's Rosetta mission have made monumental strides in studying these objects. These missions have successfully mapped their surfaces, analyzed their compositions, and even brought back material from asteroids to Earth. Each new discovery enriches our understanding of our solar system's history and moves us closer to solving the mystery of the origins of life itself. Through these space expeditions, asteroids and comets remain pivotal in our quest to decode the secrets of the cosmos. Turning our gaze further into the depths of our solar system, Saturn's rings emerge as one of the most visually stunning and scientifically intriguing phenomena in the universe. With their icy particles ranging from tiny grains to massive boulders, Saturn's rings stretch over 100,000 kilometers in diameter. Despite this vast expanse, the rings are incredibly thin, often only a few dozen meters deep. This striking contrast between their enormous reach and delicate thickness creates an almost surreal spectacle, capturing the imaginations of both scientists and stargazers for centuries. The study of Saturn's rings has provided invaluable insights into the formation and evolution of planetary systems, not just in our own solar system, but potentially across the universe. Researchers believe these iconic rings may be relatively young, perhaps formed from the remnants of moons and comets that were shattered by Saturn's immense gravity. This theory suggests that planetary rings could be a common feature of many star systems, offering us a natural laboratory to observe processes that could also be occurring in distant galaxies. Recent missions, such as NASA's Cassini spacecraft, have made it possible to examine Saturn's rings with unprecedented detail. The spacecraft revealed complex structures within the rings, including gaps, waves, and even small moonlets, which contribute to the overall dynamics of the ring system. These features highlight the forces at play, such as gravity and orbital dynamics, which shape the rings over time. One fascinating discovery is the presence of shepherd moons, small satellites that orbit near the rings, helping to keep the ring material in place. These moons prevent the rings from becoming too diffuse, orchestrating a delicate cosmic dance that continues to captivate scientists. Moreover, the study of Saturn's rings has unveiled crucial information about the nature of these icy structures, shedding light on the physical processes at work in the universe. By analyzing the composition and behavior of the particles that make up the rings, scientists have been able to make educated guesses about the history of Saturn itself, along with its moons. These findings are helping to refine our broader understanding of planetary formation, providing insights not just into the Saturnian system, but into the processes that may have shaped other planets throughout the cosmos. Saturn's rings, then, are not just a visual wonder, they are a key to unraveling some of the most profound mysteries of how planets and their systems evolve. By studying these stunning rings, we are able to peer into the past and gain a better understanding of the cosmic processes that govern planetary systems, both near and far. When we turn our attention to Mars, we encounter a planet that, in many ways, mirrors Earth. Often referred to as Earth's twin, Mars shares several key characteristics with our home planet. Both are terrestrial worlds, meaning they possess solid rocky surfaces. Both planets experience seasons, a result of their axial tilts, which causes weather patterns similar to those on Earth. Mars, too, has its own seasonal changes, marked by polar caps made of ice and frozen carbon dioxide, as well as the occasional dust storm that can sweep across the landscape. Yet, for all the similarities, Mars is starkly different from Earth in several critical ways. The most striking difference lies in the planet's atmosphere. Unlike Earth's thick, oxygen-rich atmosphere, Mars has an incredibly thin atmosphere composed almost entirely of carbon dioxide. This lack of a substantial atmosphere means that Mars cannot retain heat effectively, leading to extreme fluctuations in temperature. These can range from below freezing at night to blistering heat during the day, an inhospitable environment for life as we know it. In contrast, Earth's atmosphere, rich in oxygen and nitrogen, creates a stable environment that supports a diverse range of life. Our atmosphere not only protects us from harmful radiation, but also regulates temperature, maintaining the conditions necessary for life to thrive. The difference between these two planets highlights the importance of atmosphere in determining the habitability of a planet and raises questions about the potential for life elsewhere in the universe. Could Mars, with its striking similarities to Earth, one day host life? Or does its inhospitable atmosphere make this a distant dream? As we continue to explore both Mars and our own planet, we are constantly reminded of the delicate balance that sustains life on Earth and the unique characteristics that set other worlds apart. While Mars shares some of Earth's features, the differences in their atmospheres, climates, and geologies suggest that the evolution of life on each planet has followed radically different paths. Still, the exploration of Mars serves as a crucial step in understanding not only our own planet's history, but also the broader dynamics of planetary systems throughout the galaxy. Mars, a world that captures the imagination of scientists and dreamers alike, has long been a subject of fascination. With a diameter roughly half that of Earth, it offers a surface area comparable to Earth's dry land, sparking curiosity about its potential for past life and the conditions that may have existed there. The gravity on Mars is approximately 38% that of Earth, which means that a person standing on its surface would be able to leap much higher than they could on Earth. This lower gravity not only affects movement, but also has an impact on the planet's ability to hold onto an atmosphere, as the lack of sufficient gravity could allow lighter gases to escape into space. Mars's surface is home to some of the most remarkable geological features in our solar system. Towering above its dusty plains is Olympus Mons, an enormous shield volcano that rises about 13 miles into the Martian sky, making it the tallest volcano not only on Mars, but in the entire solar system. Its colossal size dwarfs even Earth's largest volcanoes, such as Mount Everest, and highlights the immense geological forces at play on this cold, dry world. The planet also boasts Valles Marineris, a vast canyon system that stretches for over 2,500 miles, nearly 10 times the length of the Grand Canyon on Earth. These awe-inspiring features tell the story of Mars's turbulent history, one marked by tectonic shifts, volcanic activity, and erosion. But what truly sets Mars apart is the tantalizing possibility that liquid water once flowed on its surface. While Earth is teeming with life, Thanks to its abundance of liquid water, Mars presents a different story. The planet's surface shows signs that, in the distant past, it harbored rivers, lakes, and perhaps even oceans. Ancient channels, deltas, and mineral deposits suggest that Mars may have been a much wetter and warmer world, capable of supporting life. The presence of these signs raises intriguing questions. Could life have once thrived on Mars? And if so, what happened to it? Researchers and space enthusiasts alike are drawn to Mars to explore these questions, seeking to uncover clues that may shed light on the history of our solar system and our place within it. The study of Mars provides us with a unique lens through which we can explore not only the history of our neighboring planet, but also the fundamental forces that shape all planets. Comparing and contrasting Mars with Earth deepens our understanding of the delicate balance of factors required for a planet to support life. From its atmosphere to its geology, Mars serves as a natural laboratory, offering insights into the processes that made Earth the vibrant, life-sustaining world we call home. Beyond Mars, our quest to explore the possibilities of life in our solar system takes us to the icy moon of Jupiter, Europa. This enigmatic world, with its frozen surface, is more than just a distant satellite. Beneath the thick layers of ice, there lies an ocean, vast and largely hidden from view, containing twice the volume of all of Earth's oceans combined. This subterranean sea is kept warm by tidal forces generated by Jupiter's immense gravitational pull, making it a unique and potentially habitable environment. The combination of liquid water, heat, and energy creates conditions where life as we know it could potentially thrive. Europa's surface is a dramatic sight. Its cracked, jagged ice plates seem to have been pushed and pulled by the forces below, hinting at a dynamic, ever-changing geology beneath. These movements could allow for nutrient exchange between the ocean beneath and the icy surface above, an essential process for supporting life. Additionally, organic compounds have been detected on Europa's surface. These molecules, the building blocks of life, suggest that the moon may possess all the necessary ingredients to support microbial life. Combined with liquid water and a stable energy source, Europa stands out as a prime candidate for astrobiological studies. The potential for life on Europa doesn't stop there. Scientists have speculated that Europa's ocean could harbor chemical interactions similar to those found in Earth's deep-sea hydrothermal vents, where thriving ecosystems exist despite the absence of sunlight. Instead, these ecosystems rely on the energy released by chemical reactions in the Earth's crust. On Europa, similar mineral-rich materials could seep from the moon's rocky mantle into the ocean, creating a possible oasis for microbial life. The conditions on Europa are so promising that astrobiologists and space agencies around the world are eager to investigate further. Upcoming missions, such as NASA's Europa Clipper, are poised to unlock the mysteries of this intriguing moon. Set to launch in the near future, the Europa Clipper will conduct high-resolution reconnaissance of Europa's ice shell and its subsurface ocean, searching for signs of habitability and, potentially, life. With each new discovery, we inch closer to answering one of humanity's most profound questions. Are we alone in the universe? The stakes are high, and Europa remains a central focus in our ongoing search for life beyond Earth. In the midst of this cosmic exploration, solar flares and coronal mass ejections, CMEs, serve as a reminder of the dynamic and sometimes hazardous nature of our solar environment. These eruptions, which occur on the surface of the Sun, release vast amounts of energy and charged particles into space. Solar flares are intense bursts of radiation triggered by the release of magnetic energy stored in the Sun's atmosphere, while coronal mass ejections involve the expulsion of large volumes of plasma and magnetic field from the Sun's corona. When these phenomena occur, their effects can reach Earth and disrupt our technological infrastructure. Solar flares send a surge of ultraviolet and X-ray radiation toward Earth, which can interfere with high-frequency radio communications, GPS systems, and other satellite-based technologies. In some cases, solar flares can cause temporary blackouts, disrupting critical services and communications. Coronal mass ejections, with their massive expulsion of solar material, can also impact Earth's magnetic field, leading to geomagnetic storms. These storms can wreak havoc on power grids, satellite systems, and communication networks, showing just how interconnected we are with the sun's unpredictable behavior. As our understanding of these phenomena deepens, we begin to appreciate the delicate balance between the sun's energy and the technology that sustains modern life on Earth. From the ancient mysteries of Mars to the frozen depths of Europa, and even the dangers posed by solar activity, our exploration of the solar system reveals a constantly changing, dynamic universe full of both wonder and potential peril. Each discovery, whether it's uncovering the possibility of life on another world or understanding the forces that shape our own planet, helps to bring us closer to answering some of humanity's most profound questions about the nature of life, the cosmos, and our place within it. The immense forces at play within our solar system extend far beyond the visible universe, constantly affecting the delicate balance between the Earth and its surrounding cosmic environment. When we look to the sky, we can often see the dazzling brilliance of the sun, unaware of the immense power it exerts on our planet. At times, this power manifests in dramatic ways, such as the intense solar winds and radiation emissions that arise from solar activity. These phenomena can have far-reaching consequences, particularly when a solar event such as a coronal mass ejection, CME, occurs. Coronal mass ejections are violent bursts of solar wind and magnetic fields that shoot outward from the sun. When one of these massive eruptions is directed toward Earth, the consequences can be profound. These charged particles interact with the Earth's magnetic field, triggering geomagnetic storms. These storms can wreak havoc on our planet's electrical systems, sometimes leading to widespread power outages and disrupting communication systems. In extreme cases, they could even damage satellites orbiting the planet. At higher altitudes, the solar wind can increase atmospheric density, forcing satellites to adjust their trajectories. This kind of impact is particularly concerning for astronauts in space, who face heightened radiation exposure during solar events. This makes it crucial for space missions to continuously monitor solar activity, ensuring the safety of astronauts and the proper functioning of space infrastructure. Stars themselves, whose energy sustains life on Earth, are born in vast clouds of gas and dust known as nebulae. These clouds, predominantly composed of hydrogen, stretch across light years of space. Over time, regions within these clouds can become increasingly dense due to various forces, the most prominent being gravity. As the material gathers, it forms a protostar, a dense, glowing core surrounded by a swirling disk of gas and dust. The collapse of this material under its own gravity generates immense heat and pressure, causing the protostar to heat up. This process, known as gravitational contraction, can last millions of years. Eventually, the temperature within the protostar reaches critical levels, around 15 million degrees Celsius, and nuclear fusion begins. This marks the true birth of a star. During fusion, hydrogen atoms collide with such force that they fuse together, creating helium and releasing vast amounts of energy in the process. This energy generates an outward pressure that balances the inward pull of gravity, stabilizing the star during its early stages of life. Stars can vary greatly depending on the size of the original gas cloud. Larger clouds form more massive stars, while smaller clouds give birth to smaller stars. The composition of the surrounding environment also plays a critical role in determining the characteristics of the star. Once nuclear fusion ignites, the star enters a stable phase known as the main sequence. This is where a star will spend most of its life, shining brightly across the universe and providing the necessary energy to support planets and, in some cases, life. The creation of a star is not just about lighting up the cosmos. It is also a key process in the enrichment of the universe with heavier elements. Through the later stages of stellar evolution, stars forge elements like carbon, oxygen, and iron, which are scattered into the interstellar medium when they die, creating the building blocks for new stars, planets, and even life itself. Stars begin their journey in the cold, dark regions of space, particularly in molecular clouds where gravity pulls together gas and dust. These clouds, made up predominantly of hydrogen, can be vast, spanning several light years. In these areas, clumps of material form due to gravitational attraction, leading to the creation of a protostar. Over the course of hundreds of thousands of years, the pressure and temperature at the core of the protostar increase significantly. Once conditions are right, nuclear fusion ignites and a star is born. A star's life is a delicate balancing act between energy production and gravitational pressure. The fusion reactions in the core generate an outward pressure while gravity pulls everything inward. This balance allows a star to burn brightly for millions, if not billions, of years. Smaller stars like our Sun consume their hydrogen slowly, providing a stable and long-lasting environment for life to develop. As a star exhausts its hydrogen fuel, it enters a new phase of evolution. For medium-sized stars like our Sun, once hydrogen is used up in the core, the star begins to fuse helium into heavier elements. This process causes the star to expand dramatically, eventually transforming into what we call a red giant. In contrast, massive stars undergo an even more extreme transformation, growing into supergiants. These giants shed their outer layers in spectacular explosions known as supernovae. These explosive deaths scatter the star's heavy elements across the universe, seeding the creation of new stars, planets, and even life. The final fate of a star depends largely on its mass. Low-mass stars like the Sun will shed their outer layers, leaving behind a dense core known as a white dwarf. Over billions of years, the white dwarf will cool and fade away. On the other hand, the most massive stars collapse under their own gravity after a supernova, leading to the formation of neutron stars or black holes. Stars are not just points of light in the night sky, they are the engines that power the universe. Through nuclear fusion, stars create vast amounts of energy, lighting up the cosmos and supporting life on Earth. When a star begins to fuse hydrogen atoms, they collide with such force that they overcome their natural repulsion and form helium. This process releases tremendous energy in the form of light and heat, which radiates outward from the star, sustaining its brightness. At the core of this energy production is the immense gravitational pressure, which forces hydrogen atoms close enough to interact. Once these atoms fuse, the process releases energy that counterbalances the gravitational forces pulling the star inward. This energy keeps the star stable throughout its life cycle, allowing it to shine steadily for millions to billions of years. The fusion reactions inside stars act as a powerful engine, propelling them through the various stages of their life cycles. Once a star has exhausted its hydrogen supply, it begins fusing heavier elements such as helium into carbon and even heavier elements like oxygen and iron. This process varies depending on the star's mass. More massive stars have hotter cores, enabling them to fuse elements more efficiently. Over time, the nuclear processes in these stars become more complex, producing a wide variety of elements essential for life on Earth. The energy produced through nuclear fusion in stars is crucial not only for the stars themselves, but also for the entire universe. The light and heat emitted by stars make life possible on planets and drive the formation of elements that later become part of planets like Earth. Thus, nuclear fusion is not just a process that lights up the sky, but one that shapes the cosmos and underpins the very existence of life. Stars are classified based on factors such as their size, temperature, brightness, and stage in their life cycle. Their evolution follows a predictable path from birth to death, determined by their mass and the nuclear processes happening at their core. Red giants, for example, are a fascinating phase in the life cycle of medium-mass stars. As they exhaust their hydrogen, they begin to fuse helium into heavier elements. This causes them to expand, sometimes hundreds of times the size of their original form. As they do, they give off a brilliant red glow that illuminates the surrounding space. On the opposite end of the spectrum are white dwarfs. After a red giant sheds its outer layers, it leaves behind a small, dense core, primarily composed of carbon and oxygen. This core, known as a white dwarf, no longer produces energy through nuclear fusion. However, it still shines brightly due to residual heat. Over time, it will gradually cool and fade into obscurity. The contrasting paths of red giants and white dwarfs are just a few examples of the vast diversity of stellar objects found in the universe. Each stage in the life cycle of a star contributes to the intricate balance that governs the evolution of galaxies and the formation of new stars. These cosmic processes are a testament to the complexity and beauty of the universe, where every death of a star seeds the birth of new worlds. Supernovae, the violent end of massive stars, are among the most dramatic events in the cosmos. These explosions occur when a star exhausts its nuclear fuel and collapses under its own gravity, or when a white dwarf in a binary system triggers a runaway nuclear reaction. Regardless of the cause, the result is a massive release of energy, light, and matter, often outshining entire galaxies for a brief period. Supernovae are not just visually spectacular, they are fundamental to the evolution of galaxies. When a star explodes, it releases a variety of elements forged in its core, including iron, carbon, and oxygen. These elements are the building blocks of new stars and planets. They are also essential for the formation of life as we know it, providing the raw materials from which the very atoms in our bodies are made. Thus, the birth and death of stars are more than just processes of cosmic interest. They shape the very fabric of the universe, creating the elements that make up everything we see and ensuring that the cycle of life, death, and rebirth continues throughout the cosmos. The life of a star is not just an isolated event. It is part of a grand, ongoing process that drives the creation of the universe itself. Without supernovae, the universe would be lacking many of the crucial elements needed for the formation of complex molecules. These elements, such as carbon, oxygen, and iron, are forged in the explosive heart of dying stars and scattered across the cosmos, providing the essential building blocks for life as we know it. But supernovae do much more than just create heavy elements. They play a vital role in the ongoing recycling process of the universe. The shockwaves generated by these cataclysmic events have the power to trigger the birth of new stars. As the shockwaves compress surrounding gas and dust, often containing the remnants of previous generations of stars, new stars begin to form from the very material that once composed their predecessors. This continuous cycle of star birth, death, and rebirth is a remarkable phenomenon, offering a window into the grand narrative of cosmic evolution. It also shapes the life cycle of matter itself, constantly pushing the boundaries of our understanding of the universe. One of the most fascinating aspects of supernovae is their role in cosmology. Some supernovae, particularly type Ia, serve as standard candles that astronomers use to measure vast astronomical distances. By observing the brightness of these explosions and comparing it to their known intrinsic luminosity, scientists can estimate how far away they are. This method has been instrumental in unveiling one of the most profound discoveries in modern science, the existence of dark energy. Dark energy is a mysterious force that accelerates the expansion of the universe, a discovery made possible by the observations of type Ia supernovae. Thus, supernovae do not just light up the night sky in a spectacular display. They provide key insights into the very fabric of the cosmos, helping us decipher the nature of the universe itself. The life cycle of a star is one of nature's grandest narratives, and its conclusion is no less dramatic. When a massive star reaches the end of its life, it exhausts the nuclear fuel that has kept it stable for millions or even billions of years. Unable to maintain the pressure that counteracts gravity, the star begins to collapse under its own weight. The core implodes, and temperatures soar to unimaginable levels, triggering an explosive event that ejects the star's outer layers into space. This brilliant explosion is what we call a supernova, a transient yet incredibly powerful event that can briefly outshine an entire galaxy. In the aftermath of the explosion, the core may remain, becoming extraordinarily dense. If the remaining core has a mass between approximately 1.4 and 3 times that of the Sun, gravity compresses it to such an extent that electrons and protons combine to form neutrons, resulting in what is known as a neutron star. These stellar remnants are some of the densest objects in the universe. Imagine cramming the mass of the Sun into a sphere no larger than a city. A cubic centimeter of neutron star material could weigh as much as an entire mountain. These neutron stars are not merely the remnants of dead stars. They are also cosmic laboratories, offering a glimpse into the extreme conditions of matter under immense pressure and gravity. The intense magnetic and gravitational fields around neutron stars give rise to unique phenomena. Some of these stars rotate at incredibly fast speeds, emitting beams of radiation that sweep across space like cosmic lighthouses. These rapidly rotating neutron stars are known as pulsars, and they have become a powerful tool for astrophysicists. The regular pulses of radiation they emit help scientists probe the limits of fundamental physics, and investigate the behavior of matter in conditions that cannot be replicated anywhere else in the universe. In addition to neutron stars, supernovae can also lead to the formation of black holes. If the remaining core of a supernova is massive enough, collapsing beyond a certain threshold, the gravitational force becomes so intense that nothing, not even light, can escape. This leads to the creation of a black hole, a region of space where gravity is so strong that it warps the fabric of space-time itself. These transformations, whether leading to neutron stars or black holes, illustrate a crucial cosmic principle. The death of stars is not an end, but a transition that leads to the creation of new, more exotic structures. This process of creation and destruction is a fundamental part of the ongoing cycle that shapes our universe. The intricate dance of life and death in the cosmos reveals the profound interconnectedness of all celestial objects. From the violent explosion of a supernova to the birth of a neutron star or a black hole, these processes demonstrate the principle that from chaos often comes new order. Pulsars in particular embody this principle. These highly magnetized, rapidly rotating neutron stars emit beams of electromagnetic radiation from their magnetic poles. As the beams sweep across space, they can be detected from Earth as regular pulses of radiation. This behavior is akin to a lighthouse sending out a rhythmic flash of light across the sea. The pulsation is the result of the star's rapid rotation. Some pulsars spin several times each second. Pulsars were first discovered in the late 1960s, and their nature was initially a mystery. The first pulsar, known as LGM-1, Little Green Men 1, was detected by Jocelyn Bell Burnell and Anthony Hewish. At first, the regularity of the pulses led some astronomers to speculate that they might be signals from extraterrestrial civilizations. However, it soon became clear that these pulses were not of artificial origin. Pulsars are the remnants of supernova explosions, marking the death of massive stars and the birth of incredibly dense objects with a mass greater than the Sun, but confined within a sphere just about 20 kilometers across. As cosmic lighthouses, pulsars have become invaluable tools for astronomers. Their predictable pulses provide a reliable cosmic clock, allowing scientists to study a variety of astrophysical phenomena. By precisely measuring the intervals between these pulses, astronomers can measure interstellar distances with remarkable accuracy. Pulsars have also been used to test theories of gravity, especially in the search for gravitational waves. Their regular emissions serve as an extraordinarily precise timekeeping system, which has proven invaluable in the study of the cosmos and the laws that govern it. Through the study of pulsars and other remnants of supernova, scientists continue to unlock the mysteries of the universe. These phenomena offer a glimpse into the fundamental processes that govern the birth, life, and death of stars, and they reveal how the cycle of stellar evolution shapes the universe around us. In this vast cosmic landscape, the death of a star is not an end, but a beginning, a new chapter in the endless story of creation and transformation. Pulsars, with their fascinatingly precise and rhythmic rotations, are far from just celestial beacons. These rotating neutron stars, born from the collapse of massive stars, interact with their environments in complex and intriguing ways, creating phenomena such as pulsar wind nebulae. These are clouds of charged particles ejected as the pulsar spins, creating intense magnetic fields and energetic winds that ripple through the surrounding space. The study of these phenomena opens up a deeper understanding of not only the pulsars themselves, but also the intricate dynamics of the universe around them. These celestial lighthouses, pulsars, serve as a guide for astronomers, offering invaluable insights into the life cycles of stars, the behavior of matter under extreme conditions, and the fundamental forces of nature. As they sweep their beams of radiation across vast distances, pulsars allow scientists to measure things such as space-time distortions and magnetic field strengths, offering key clues about the universe's underlying mechanics. Their study has far-reaching implications, revealing hidden aspects of astrophysics and the nature of the cosmos itself. Pulsars aren't just cosmic curiosities, they also help unravel secrets about the fabric of the universe. Through their interactions with surrounding matter and the intense magnetic fields they generate, they provide researchers with opportunities to explore some of the most extreme and enigmatic aspects of astrophysics, such as the behavior of light in strong gravitational fields. The more we study these phenomena, the more we can understand the nature of forces like gravity and electromagnetism, pushing the boundaries of our scientific knowledge. In the search for new worlds, the detection of exoplanets, planets orbiting stars beyond our solar system, has opened an entirely new chapter in the exploration of the cosmos. This pursuit has been nothing short of transformative, fundamentally altering our perception of the universe and our place within it. To identify these distant worlds, scientists employ a variety of sophisticated methods, each offering unique insights into the characteristics of far-off planets. One of the most widely used techniques is the transit method, where astronomers observe the light of a distant star and monitor how it dims when a planet passes in front of it. This seemingly simple event allows scientists to calculate key properties of the planet, such as its size, orbital period, and sometimes even the nature of its atmosphere. The dimming is subtle but measurable, and by carefully monitoring this phenomenon over time, researchers can detect planets with remarkable precision. This method also provides crucial information on whether a planet resides in the habitable zone, the region around a star where conditions may be suitable for liquid water to exist, an essential factor for the development of life as we know it. Another powerful technique is the radial velocity method, often referred to as the Doppler wobble technique. This method detects the gravitational pull exerted by an orbiting planet on its host star, causing the star to wobble slightly. This wobble alters the star's light, shifting its spectrum towards the red or blue ends, depending on whether the star is moving away from or towards us. By analyzing these shifts, astronomers can infer the presence of an exoplanet and even estimate its mass. The slight back and forth motion of the star is subtle but incredibly revealing, offering valuable data on the planet's orbit and potential for supporting life. Beyond these primary methods, astronomers also turn to direct imaging and gravitational microlensing, two techniques that offer a more direct view of exoplanets. Direct imaging, while difficult due to the overwhelming brightness of stars, involves capturing actual photographs of planets themselves. This technique is invaluable in studying distant exoplanets, offering insights into their atmospheres, compositions, and even surface features when conditions allow. Gravitational microlensing, on the other hand, takes advantage of the gravitational lensing effect, where the gravity of an exoplanet magnifies the light of a more distant star. This temporary brightening provides a telltale sign of a planet's presence, enabling astronomers to detect exoplanets even if they are far too faint to observe directly. As technology continues to advance, particularly with the advent of space-based telescopes like the Transiting Exoplanet Survey Satellite, TESS, and the James Webb Space Telescope, JWST, our ability to detect and study these distant worlds grows exponentially. These powerful instruments allow us to peer deeper into space, observing the faintest stars and planets and gathering unprecedented data on their characteristics. With these technological advancements, our understanding of exoplanets has expanded, revealing new and exciting possibilities for the existence of life beyond Earth. The search for exoplanets has not only expanded our knowledge of how planets form and evolve, but has also ignited a curiosity about the potential for life elsewhere in the universe. One of the most exciting aspects of this research is the focus on finding exoplanets that may be habitable, where conditions might be suitable for life. The primary focus here is on planets that exist within the habitable zone of their stars, where temperatures could allow for the presence of liquid water, a fundamental ingredient for life. The transit method remains a powerful tool in this search, offering insights into the size, orbital period, and potential habitability of planets. By observing multiple transits of a planet across its star, scientists can determine whether the planet lies within the habitable zone, the region where conditions may be just right for life to thrive. If a planet is found in this zone, it becomes a prime candidate for further study, with researchers eager to explore its potential for supporting life. Similarly, the radial velocity method provides essential clues about a planet's characteristics and its potential habitability. By studying the star's motion caused by the gravitational influence of its orbiting planet, astronomers can estimate the planet's mass and orbital properties, both of which are crucial factors in determining whether a planet might support life. This information is used to prioritize which planets to study further, allowing scientists to focus their efforts on the most promising candidates. Direct imaging, too, plays a significant role in the hunt for habitable worlds. By capturing detailed images of exoplanets, astronomers can analyze their atmospheres and compositions, searching for chemical signatures that might indicate the presence of life. Gases like oxygen, methane, and carbon dioxide, when detected in an exoplanet's atmosphere, could signal biological activity, marking the planet as a potential candidate for habitability. This technique has the potential to revolutionize our understanding of exoplanets, offering direct evidence of their characteristics and their ability to support life. Finally, the upcoming launch of the James Webb Space Telescope promises to push the boundaries of our search for habitable exoplanets. Equipped with advanced instruments capable of observing the infrared spectrum, the JWST will allow astronomers to study smaller Earth-like exoplanets in unprecedented detail. By analyzing the atmospheres of these planets, scientists hope to uncover crucial information about their climates and their potential to support life. In combination, these methods are paving the way for groundbreaking discoveries in the search for life beyond Earth. As we continue to refine our tools and techniques, we move ever closer to answering one of humanity's oldest and most profound questions. Are we alone in the universe? The quest for exoplanets, particularly those that may be habitable, represents one of the most exciting frontiers in modern science, with the potential to reshape our understanding of life and its place in the cosmos. When studying exoplanets in the search for life, scientists focus on several key characteristics that align with our understanding of what makes Earth a hospitable environment. The most critical factor is a planet's location within the habitable zone, the region around a star where temperatures are suitable for liquid water to exist on the planet's surface. Since water is essential for life as we know it, this factor is paramount in determining a planet's potential for habitability. But location alone is not enough. The composition and atmosphere of an exoplanet also play vital roles in determining its ability to support life. A planet's atmosphere must be rich in the necessary elements like oxygen and nitrogen, which not only provide the potential for life forms, but also protect them from harmful radiation. Without such an atmosphere, life as we understand it would not be possible. Therefore, astronomers consider both the position of a planet and the composition of its atmosphere when evaluating its potential for supporting life. Together, these factors help guide the ongoing search for habitable exoplanets, offering new possibilities for the future of space exploration and the potential discovery of extraterrestrial life. The search for exoplanets capable of supporting life hinges on a delicate interplay of numerous factors, each contributing to the potential for life beyond Earth. One of the most crucial elements in this equation is the planet's composition. For a world to support life as we know it, a solid surface made of rock, much like Earth's, is essential. Such a composition increases the likelihood of ecosystems forming, environments capable of sustaining diverse life forms, from microscopic organisms to more complex life. Earth's rich geological makeup provides the foundation for life's evolution, and exoplanets with similar properties would hold the promise of ecosystems thriving under comparable conditions. Equally important is the size and gravity of the exoplanet. An ideal candidate for life would closely resemble Earth in these respects. The planet must be large enough to maintain a stable atmosphere, a crucial factor in protecting life from harmful radiation and regulating temperatures. Gravity, too, must be just right. Not too weak to let the atmosphere escape into space, but not too strong to crush potential life forms. This delicate balance ensures that the planet can support an environment where life could flourish. While larger planets might boast thicker atmospheres, there's a tipping point. If a planet becomes too massive, it might pull in excessive amounts of gas from its surroundings, leading to an inhospitable environment for life as we understand it. Thus, the ideal exoplanet mirrors Earth's size and gravity, creating a perfect setting for life to take root. Another critical factor in this search is geological activity, which plays a pivotal role in maintaining the stability of a planet's environment. Planets exhibiting tectonic movement and volcanism have the ability to recycle nutrients and regulate their climates. This dynamic geological activity ensures that the planet's surface remains fresh and that essential nutrients are continually replenished. Without such activity, a planet's surface could become stagnant, limiting the variety of habitats and climates that are necessary to sustain life. A world that experiences ongoing geological change can create diverse ecosystems with shifting landscapes and varying environments that increase the potential for life to adapt and evolve in different ways. When we put all these elements together, composition, size, gravity, and geological activity, they form a complex equation guiding scientists in their quest to identify exoplanets with the potential to harbor life. The search becomes not just a hunt for planets similar to Earth, but an investigation into the many conditions that might allow life to arise elsewhere in the cosmos. But what if life isn't as dependent on Earth-like conditions as we once thought? The study of extremophiles, organisms that thrive in the most inhospitable environments on Earth, has transformed our understanding of biology. These extraordinary creatures exist in conditions previously believed to be impossible for life to endure. From the extreme pressures and scorching temperatures of deep-sea hydrothermal vents, to the acidic, boiling waters of hot springs, to the frozen, barren landscapes of Antarctica, extremophiles have adapted to survive where most life forms would perish. Their ability to withstand intense radiation, extreme cold, and crushing pressure challenges our assumptions about the conditions required for life. By studying these resilient organisms, scientists have gained invaluable insights into the fundamental requirements for life. For example, certain extremophiles, such as specific bacteria, can metabolize sulfur or nitrogen, chemicals that are abundant in environments lacking sunlight and brimming with minerals. These adaptations suggest that life could survive in extraterrestrial environments where sunlight is scarce or absent. Places like the subsurface oceans of Europa, Jupiter's icy moon, or the methane lakes on Titan, Saturn's largest moon, might host life forms that survive in ways we never before considered. Such discoveries broaden the possibilities for life beyond Earth, showing us that our planet's conditions may not be the only recipe for life's existence. The implications are profound. As we continue to explore the cosmos and search for other Earth-like planets, our understanding of life itself is evolving. Life, it turns out, might not require a familiar environment at all. It might thrive in places we once thought were inhospitable, pushing the boundaries of what we consider possible. The study of extremophiles has opened the door to a future where we can begin to imagine life in forms and environments vastly different from our own and perhaps just beyond our reach. A new chapter in the story of life in the universe is waiting to be written. Extremophiles, organisms that thrive in environments previously considered hostile to life, offer extraordinary insights into the adaptability and resilience of life forms. These remarkable creatures are not just survivors, they are pioneers, showing us the incredible flexibility that life can exhibit under the most extreme conditions. Their existence suggests that life could arise and evolve in forms we have yet to imagine, utilizing energy sources and biochemical processes far beyond our current understanding. This versatility challenges the very notion of what constitutes a habitable zone and expands our search for life to places we may never have previously considered. One of the most fascinating ideas that emerges from the study of extremophiles is the theory of shadow biospheres. This hypothesis proposes that life forms, completely different from the ones we know, may exist right under our noses, yet remain unnoticed because they thrive in environments as alien as the harshest conditions on Earth. These life forms may not even require the traditional conditions we associate with life, such as oxygen and sunlight. Their existence could fundamentally alter our perceptions of life itself, suggesting that we have only scratched the surface of what is possible in the vast expanse of the universe. As scientists continue to study extremophiles, they deepen our understanding of life's resilience on Earth, while simultaneously fueling the search for life elsewhere. These organisms provide valuable clues that inform the ongoing quest for extraterrestrial life, reaffirming the belief that we have only just begun to uncover the endless possibilities of existence beyond our own planet. Their discovery is not just about exploring new life forms, but about reshaping our understanding of what life can be. The Kepler mission, launched in 2009, revolutionized our comprehension of the universe and its potential for supporting life. By focusing on a small patch of sky in the constellation Cygnus, Kepler used a technique known as transit photometry to measure the faint dip in a star's brightness when a planet passed in front of it. This breakthrough allowed scientists to identify thousands of exoplanets, planets orbiting stars outside our solar system, and confirmed what many had suspected. Planets are far more abundant in our galaxy than we ever imagined. Kepler's discoveries forced scientists to reconsider the traditional models of planetary formation, challenging old assumptions about how planets evolve and what makes a world habitable. Perhaps the most exciting revelation from the Kepler mission was the discovery of Earth-sized and super-Earth-sized planets located within the habitable zone of their stars. This zone is the region around a star where conditions might be just right for liquid water to exist, a critical ingredient for life as we know it. Kepler's findings suggested that about 20% of Sun-like stars have planets in this zone, implying that potentially habitable worlds are far more common than we had previously thought. This ignited a renewed fervor in the search for extraterrestrial life, driving the scientific community to explore the atmospheres of these distant planets for signs of life or biosignatures. Following in Kepler's footsteps, the Transiting Exoplanet Survey Satellite, TSS, launched in 2018, expanded the search for exoplanets to a much broader area. While Kepler focused on a small patch of sky, TESS surveys the entire sky over a 2-year period. Its primary goal is to identify bright nearby stars with transiting exoplanets, planets that pass in front of their stars from our point of view, making them prime candidates for further investigation. TESS has already discovered thousands of planet candidates, significantly contributing to our growing catalog of exoplanets. Its focus on bright stars allows for more detailed study with ground-based telescopes, pushing the boundaries of what we know about distant worlds. Together, these missions represent a paradigm shift in the way we approach cosmology and the search for life beyond Earth. With the staggering statistical evidence now at our disposal, humanity stands at the brink of understanding not only our own solar system, but also the diverse array of planets that populate our galaxy. The excitement surrounding these discoveries is not just in the numbers, it's in the infinite possibilities they present for future exploration, and more importantly, for the discovery of life elsewhere in the universe. In our own solar system, the search for extraterrestrial life is focused on 2 particularly intriguing locations, Mars and Europa. Mars, with its rocky surface and polar ice caps, has long been considered one of the most promising places to look for signs of life. Multiple missions, including NASA's Perseverance rover, are equipped with sophisticated instruments designed not only to study the Martian geology and climate, but also to search for evidence of past microbial life. Perseverance is currently collecting samples from ancient river deltas and craters, regions where signs of ancient life may be preserved, potentially revealing that life once flourished on the red planet. Europa, one of Jupiter's largest moons, presents a completely different but equally compelling environment. Beneath its icy surface lies a vast ocean of liquid water, a crucial ingredient for life as we know it. The upcoming Europa Clipper mission, launched by NASA, is set to explore Europa in unprecedented detail. Equipped with a suite of scientific instruments, the spacecraft will study the moon's ice shell, analyze its ocean's potential for habitability, and look for signs of organic materials. The mission will also monitor Europa's geologic activity, further investigating its potential to support life. Both Mars and Europa are being explored using multi-layered strategies, combining orbiters, landers, and rovers equipped with advanced detection tools. These missions focus on astrobiology, the study of life in extreme environments, providing valuable insights into whether these celestial bodies could once have harbored life. Mars offers an array of terrains that suggest ancient water flow, hinting at a once habitable environment. Europa, on the other hand, boasts an ocean that could be in contact with a rocky mantle, creating conditions that might support life. As these missions continue to unfold, the synergy of data gathered from both worlds will help scientists form a clearer picture of the potential for life in our own solar neighborhood. Whether life emerges from the dry canyons of Mars or the icy depths of Europa, the search for extraterrestrial life is one of the most exciting and profound endeavors in science. With every discovery, we move closer to understanding our place in the universe and the tantalizing possibility that we are not alone. Astrobiology, the study of the origins, evolution, distribution, and future of life in the universe, is a rapidly growing field that combines biology, chemistry, geology, and astronomy. It seeks to answer some of humanity's most profound questions. What are the fundamental requirements for life? What environments might harbor life? And most intriguingly, can we detect signs of extraterrestrial organisms? A key area of astrobiological research is the study of extreme environments here on Earth. By studying organisms that thrive in places previously thought to be inhospitable, such as deep-sea hydrothermal vents, Arctic glaciers, and acidic lakes, scientists can gain insights into the types of life that could exist elsewhere in the cosmos. These organisms, known as extremophiles, challenge our traditional definitions of life and broaden the scope of what we consider habitable. They provide vital clues for understanding how life might arise and persist in environments that would be fatal to most forms of life on Earth. The search for extraterrestrial life also extends to a number of celestial bodies within our own solar system. Europa, with its icy crust and subsurface ocean, presents a tantalizing possibility for life, while Mars, with its ancient riverbeds and lakebeds, offers evidence that life may once have existed there. The study of exoplanets, planets orbiting stars far beyond our solar system, is another key area of research. Using advanced telescopes, scientists can now analyze the atmospheres of distant exoplanets, looking for chemical signatures that suggest the presence of life. Through missions to distant planets, laboratory simulations, and theoretical models, astrobiology is helping to build an empirical framework for understanding the myriad possibilities for life in the universe. As humanity continues its search for life beyond Earth, the field serves as a constant reminder of our place in the cosmos and the wonder of exploring what may lie out there, waiting to be discovered. The challenge of communicating with extraterrestrial civilizations is a monumental one. The vastness of space itself poses significant obstacles. The distances between stars and galaxies are staggering, and even if a signal were sent from a distant civilization, it could take thousands or even millions of years to reach us. This means that the timing of our existence must coincide with the existence of other civilizations capable of communication, a rare synchronicity given the age of the universe. Nonetheless, the dream of connecting with intelligent life beyond our planet continues to captivate the human imagination, driving our ongoing exploration of the cosmos. The issue of technological disparity presents a daunting challenge when we consider the possibility of advanced extraterrestrial civilizations. These civilizations may be communicating using methods that are entirely outside the realm of our comprehension. It's conceivable that they have developed technologies or scientific principles that are still beyond our reach, systems we have yet to discover or even theorize. Our efforts to detect signals from such civilizations are limited by our own understanding of the universe, which remains constrained by the laws of physics as we currently know them. Imagine for a moment that a civilization is using advanced concepts like quantum communication or even forms of signaling that extend beyond electromagnetic waves, methods that could seem completely foreign to us. Even if their signals were right before us, we might not be able to recognize them as such, let alone decode their meaning. In this scenario, our technological limitations would effectively prevent us from perceiving the signals, even though they may be all around us. Then there's the challenge of language, an even more profound barrier. If we were to receive a signal, understanding it would require a common frame of reference. Picture a civilization from an entirely different environment, with no shared experiences, no common context, and perhaps even an alien way of thinking. The symbols, sounds, or concepts they use in their communication could be entirely unintelligible to us. Creating messages that are universally interpretable is no small feat, and it's a challenge that scientists have only begun to address. One of the most notable attempts to bridge this gap is the Voyager Golden Record, a project designed to encapsulate the essence of humanity and communicate it to potential extraterrestrial listeners. Yet, even with such efforts, the question remains: how can we create a message that speaks across the vastness of space and time in a way that a distant civilization could understand? Lastly, we must confront the possibility that we simply aren't looking in the right places. The search for extraterrestrial intelligence, SETI, as it's known, predominantly focuses on specific wavelengths of electromagnetic radiation. But this approach assumes that extraterrestrial civilizations would use similar communication methods to our own, a premise that may be wildly inaccurate. What if other civilizations are using entirely different means of communication, ones that we haven't even thought to consider? The universe, with its infinite mysteries, is full of surprises, and each step in our search brings up new questions. We are reminded time and time again of the challenges that lie ahead in our quest to explore the cosmos. One of the most intriguing tools in this quest is the Drake equation. Developed in the early 1960s by astrophysicist Frank Drake, this equation was designed to estimate the number of active, communicative extraterrestrial civilizations in our galaxy. While the equation doesn't provide definitive answers, it serves as a framework for understanding the complex interactions of various factors that could contribute to the emergence of intelligent life beyond Earth. At its core, the Drake equation considers elements like the rate of star formation in our galaxy, the fraction of those stars that have planetary systems, and the number of planets capable of supporting life. It even factors in the probability of life arising on those planets and the likelihood that life will evolve into intelligent, communicative beings. Each of these variables introduces an element of uncertainty, reflecting the unknowns inherent in our search for extraterrestrial life. Scientists often point out that the values we assign to the factors in the equation are speculative. These values can vary widely, depending on new discoveries or shifts in our understanding of biology and the cosmos. Take, for example, the rapidly evolving field of exoplanet research. In recent years, astronomers have discovered thousands of planets outside our solar system, which has forced scientists to rethink previous estimates of how many of these worlds might support life. The discovery of these planets challenges earlier assumptions and inspires new questions about the prevalence of life in the universe. Despite its speculative nature, the Drake equation serves not just as a tool for calculation, but as a catalyst for ongoing discussion within the scientific community. It embodies humanity's profound curiosity about its place in the cosmos. Even as the numbers shift and new data emerges, the equation invites us to explore new avenues of research, all the while deepening our understanding of the factors that might lead to the rise of intelligent beings in distant star systems. Through the questions it raises, the Drake equation propels us forward in our never-ending quest to explore the unknown, urging us to keep looking for answers. One of the most profound discoveries that could be made in our search for extraterrestrial life would be the detection of microbial life beyond Earth. Such a discovery would dramatically alter our understanding of biology and the origins of life. If even the simplest forms of life were found elsewhere in the cosmos, it would suggest that life might be far more common than we once believed. The implications would be far-reaching, fundamentally challenging the notion that Earth is unique in its ability to sustain life. This would spark new debates about the conditions required for life to thrive and how adaptable organisms can be in extreme environments. But the consequences of finding alien life would extend far beyond scientific curiosity. The ethical dilemmas of such a discovery would be immense. How should humanity approach the study of extraterrestrial microbes? Would we take steps to protect these life forms from contamination, ensuring that they are not harmed by our presence? Or alternatively, would we eagerly study them, seeking insights into the very origins of life on Earth? These questions would challenge our ethical frameworks and perhaps force us to rethink our approach to life, both on our own planet and beyond. The discovery of microbial life elsewhere would not only redefine our understanding of biology, but also our responsibility as stewards of life in the universe. The discovery of extraterrestrial life, especially microbial life, holds profound implications across various fields, extending far beyond mere scientific curiosity. Moreover, such a discovery would likely stir significant cultural, philosophical, and religious discussions, reshaping humanity's understanding of its place in the universe. The existence of alien life would challenge long-held beliefs, prompting debates about the origins of life, our purpose in the cosmos, and the nature of intelligence itself. This discovery could also accelerate progress in space exploration. Currently, missions to Mars, Europa, and Enceladus are already aimed at uncovering signs of microbial life on these distant worlds. These explorations focus on determining whether these environments, which may have once supported or still support life, could hold the key to understanding life beyond Earth. Should we discover life, even in its most primitive form, it would likely trigger a wave of new funding, stimulating fresh interest in missions to previously uncharted regions of our solar system and beyond. As the search for life continues, it may also prompt the development of new technologies designed specifically to detect and study life in extreme conditions. The challenges of studying life on distant planets or moons would inspire innovations in sensors, instruments, and spacecraft, pushing the boundaries of what we can explore and comprehend. The lessons learned could have tangible benefits on Earth, particularly in fields such as medicine, agriculture, and climate resilience. By studying how microbes survive and adapt in harsh environments, we could gain insights into how life on Earth could adapt to changing conditions, be it due to climate change, pandemics, or other global crises. Ultimately, the search for microbial life is not just an exploration of outer space, but a quest that could redefine life here on Earth. By investigating alien life forms, we stand to unlock a wealth of knowledge that may not only explain how life began, but also offer solutions to the challenges we face on our own planet. Equally fascinating is the ongoing search for extraterrestrial intelligence, or SETI, Search for Extraterrestrial Intelligence, which seeks to detect signals from intelligent civilizations beyond our planet. At the core of SETI's efforts are radio telescopes, advanced instruments designed to listen for radio waves traveling through space. These telescopes are capable of detecting a wide range of frequencies, especially in the microwave band, where scientists hypothesize alien transmissions might be detected. By focusing on particular stars or regions of space with the potential for habitable planets, SETI researchers analyze enormous volumes of data, scanning the cosmos for unusual patterns that might indicate the presence of intelligent life. SETI scientists employ a range of sophisticated technologies, including advanced algorithms and software, to sift through the vast amounts of data they collect. These algorithms help filter out natural interference, such as cosmic radiation and man-made signals, honing in on anything that could be artificial. One notable SETI project involves the use of multiple telescopes working in tandem, pooling their efforts to increase the chances of detecting a signal. By combining data from different sources, these networks of telescopes can cover a broader swath of the sky and monitor more frequencies, increasing the probability of identifying something truly remarkable. Some SETI researchers take advantage of existing facilities, such as the Arecibo Observatory in Puerto Rico or the Green Bank Telescope in West Virginia, to extend their observational reach. These powerful telescopes help scientists explore vast stretches of space for potential signals from distant civilizations. In recent years, SETI's scope has expanded to include optical signals, specifically laser pulses that might be emitted by advanced extraterrestrial civilizations. This shift broadens the search beyond traditional radio waves, allowing scientists to explore the full spectrum of potential communication methods, including those that might be more technologically advanced or rare. This more comprehensive approach continues to drive excitement and curiosity in the search for intelligent life, underscoring the idea that the universe is vast and the search for our cosmic neighbors must be as thorough as possible. SETI's quest for extraterrestrial intelligence has made tremendous progress in recent years, largely thanks to advancements in technology. A significant step forward is the ongoing construction of the Square Kilometre Array, SKA, a massive radio telescope being built in both Australia and South Africa. When completed, the SKA will be the largest radio telescope in the world, combining thousands of individual antennas spread across a vast area to capture faint signals from space. This ambitious project will significantly enhance our ability to detect signals from alien civilizations, expanding our search capabilities far beyond what was previously possible. Beyond the advances in observational tools, breakthroughs in computer science and data processing have also played a crucial role in SETI's progress. The development of powerful algorithms allows researchers to analyze the signals captured by telescopes more efficiently than ever before. These algorithms are adept at filtering out background noise and identifying potential patterns that could indicate artificial origins. Machine learning techniques further augment this process by predicting the characteristics of potential signals, distinguishing between natural cosmic phenomena and signals that might be intentionally sent by extraterrestrial civilizations. Additionally, new space missions contribute to the ongoing search for extraterrestrial intelligence. The James Webb Space Telescope, for instance, has provided unprecedented clarity in studying exoplanets, planets that orbit stars beyond our solar system. By analyzing the atmospheres of these distant worlds for biosignatures, such as oxygen or methane, scientists can gain crucial insights into the potential for life elsewhere in the universe. These missions are not limited to exoplanets, however. Space probes designed to study moons like Europa and Enceladus, which are thought to harbor subsurface oceans, also target environments that could potentially host microbial life beneath their icy surfaces. Thus, as we continue to push the boundaries of space exploration, each discovery, no matter how small, adds a new piece to the puzzle of our existence in the vast cosmos. The search for microbial life and extraterrestrial intelligence is more than a scientific endeavor. It is a deeply philosophical and existential journey that could reshape our understanding of life, intelligence, and the universe itself. Global collaboration among scientists has significantly accelerated the search for extraterrestrial intelligence, with groundbreaking initiatives such as the Breakthrough Listen project leading the charge. This ambitious project harnesses the collective resources of academia, industry, and private entities, uniting forces to monitor our galaxy in an unprecedented and comprehensive manner. Every technological advancement brings us closer to unraveling the mysteries of the universe, expanding our understanding of the unknown, and pushing the dream of discovering intelligent life beyond Earth into the realm of possibility. With each leap in technology, whether through advanced data analysis, innovative missions, or strengthened international cooperation, the quest to find extraterrestrial life is not only alive, but thriving. Space telescopes have revolutionized our ability to observe and comprehend the universe by overcoming the limitations faced by traditional ground-based observatories. One of the most significant advantages of space telescopes is that they operate above the Earth's atmosphere. This is essential because the atmosphere distorts and absorbs the light from distant objects, blurring our images and hindering our observations. Ground-based telescopes are subject to interference caused by weather conditions, air pollution, and atmospheric turbulence, factors that compromise the clarity and accuracy of the data they gather. In contrast, telescopes placed in space enjoy a clear, unobstructed view of the cosmos, allowing scientists to capture more accurate and detailed observations. Furthermore, space telescopes can access a broader range of wavelengths that are otherwise hindered or completely blocked by Earth's atmosphere. For example, infrared and ultraviolet wavelengths are essential for observing various celestial phenomena, yet the atmosphere absorbs or scatters these wavelengths, preventing ground-based telescopes from capturing them. Space-based observatories, however, can observe these wavelengths without restriction, enabling astronomers to study the formation of stars, the evolution of galaxies, and even the discovery of exoplanets in ways that were previously impossible. Another crucial benefit of space telescopes is their ability to provide continuous observation periods. On Earth, The observation windows of ground-based telescopes are limited by factors such as day-night cycles, unpredictable weather, and other environmental conditions. In space, however, these telescopes can monitor the same region of the sky for extended periods without interruption. This continuous viewing capacity is invaluable for tracking transient cosmic events like supernova explosions or the passage of asteroids, offering unparalleled detail and insight. Moreover, space telescopes often collaborate with one another, creating a network of synchronized observations that enriches the data collected. Multiple telescopes can focus on the same celestial event, each observing it through different wavelengths. This simultaneous, multifaceted approach to data collection results in a more complete and nuanced understanding of cosmic phenomena, leading to a richer interpretation of the universe's many mysteries. These technological advancements have truly transformed modern astronomy. Space telescopes have brought distant and enigmatic objects within reach, offering a closer look at the wonders of the universe and revealing new dimensions of cosmic phenomena that were once beyond our grasp. In addition to space telescopes, radio telescopes play an equally crucial role in expanding our knowledge of the cosmos. Unlike optical telescopes, which rely on visible light, radio telescopes capture radio waves emitted by celestial objects. This capability opens up an entirely different dimension of discovery, enabling astronomers to study phenomena that are invisible to the naked eye. Through radio waves, scientists have gained profound insights into a range of cosmic phenomena, from the cosmic microwave background radiation, the faint afterglow of the Big Bang, to pulsars and distant galaxies. One of the key advantages of radio telescopes is their ability to penetrate dust and gas that often obscure our view in the optical spectrum. This unique ability allows scientists to explore the complex structures within galaxies, providing a clearer understanding of star formation and the hidden dynamics at play within regions of space that are typically concealed from view. For example, within our Milky Way galaxy, radio telescopes can map the regions where stars are born, revealing the influence of supermassive black holes at the centers of galaxies. Radio telescopes have also been instrumental in the study of some of the most intriguing and powerful objects in the universe, such as quasars. These distant sources of intense radio waves provide valuable information about the early universe and the formation of large cosmic structures. By analyzing the radio emissions from quasars, scientists can gain deeper insight into the physical processes occurring in these extreme environments, offering clues about the nature of matter and energy in the early stages of the cosmos. Through the combined power of space telescopes, radio telescopes, and international collaboration, our understanding of the universe continues to expand. Each new discovery brings us closer to answering some of humanity's oldest questions. Are we alone in the universe? What lies beyond the stars? And how did the cosmos come to be the way it is today? With every breakthrough, we are reminded that the search for knowledge is an ongoing journey, one that unites scientists from around the globe in the shared pursuit of understanding the vast, complex, and awe-inspiring universe that surrounds us. Radio astronomy, while traditionally associated with exploring distant celestial phenomena, extends far beyond the confines of space observation. It plays a pivotal role in shaping technologies that profoundly impact life on Earth. This includes innovations in telecommunications, radar systems, and countless other applications that rely on radio waves. In fact, radio telescopes have become a bridge that connects the known to the unknown, enabling us to explore the farthest reaches of the universe while simultaneously contributing to advancements in technology. Through their remarkable ability to capture radio waves from distant cosmic objects, these telescopes have expanded our understanding of the universe's vast evolution, revealing secrets once hidden from our view. In recent years, cutting-edge advancements in technologies like adaptive optics and interferometry have revolutionized the way we observe the cosmos. Adaptive optics, in particular, addresses one of the biggest challenges in ground-based astronomy, the distortion caused by Earth's atmosphere. Earth's atmospheric layers create turbulence, making it difficult for telescopes to produce sharp, clear images of distant stars and galaxies. However, with the help of deformable mirrors that can adjust in real time, astronomers now have the ability to correct these distortions, achieving image clarity that was once thought to be the exclusive domain of space-based telescopes. Thanks to this breakthrough, blurry images are now replaced by strikingly detailed views of objects light years away. Interferometry, another transformative technique, takes a different approach by combining the light from multiple telescopes to achieve higher resolution than a single telescope could ever produce. By linking together various telescope arrays, astronomers can simulate the effect of a much larger observational aperture. This allows for far more detailed exploration of distant phenomena, such as binary star systems, exoplanets, and the intricate structures of galaxies far beyond our reach. The ability to combine the data from multiple telescopes has shed light on the composition, structure, and physical properties of celestial bodies, some of which were once shrouded in mystery. Together, adaptive optics and interferometry have opened new windows into the cosmos, enabling researchers to make unprecedented discoveries. These technologies have allowed astronomers to detect faint light emitted by planets orbiting distant stars, an extraordinary milestone in the search for extraterrestrial life. Adaptive optics, in particular, has provided an unparalleled opportunity to explore the surfaces of planets within our own solar system. Through this technology, scientists have gained deeper insights into the geological features and atmospheric compositions of these planets, expanding our understanding of their potential for supporting life. Looking toward the future, the refinement of adaptive optics and interferometry promises even greater discoveries. Scientists and engineers are constantly developing new instruments and techniques that push the limits of what is possible in the realm of astronomical research. As technology continues to evolve, we edge ever closer to answering some of the most profound questions about our universe, its origins, its evolution, and the possibility of life existing beyond Earth. The cosmos is becoming clearer, and humanity is just beginning to peel back the layers of the universe's mysteries. One of the most exciting technological advancements in space exploration is the James Webb Space Telescope, JWST, often referred to simply as Webb. This next-generation observatory marks a monumental leap in humanity's quest to explore the universe. Set to be the premier observatory of the coming decade, Webb's primary mission is to study the cosmos in unparalleled detail. Unlike its predecessors, Webb operates in the infrared spectrum, a feature that allows it to peer through the cosmic dust and gas that often obscure celestial objects from our view. This unique ability will unlock the secrets of the earliest galaxies that formed after the Big Bang, providing insights into the very beginning of the universe. One of Webb's most exciting goals is to investigate the birth of stars and planetary systems. By observing the dense clouds of gas and dust in which new stars are formed, Webb will provide critical information about stellar evolution and the processes that lead to the formation of planets. Understanding how planetary systems form is not only crucial for studying our own solar system, but is also key to exploring the potential for life beyond our planet. Webb's observations could offer clues about the environments in which life might thrive elsewhere in the universe. In addition to studying star formation, Webb will also focus on the study of exoplanets, planets located outside of our solar system. Equipped with state-of-the-art instruments, the telescope will analyze the atmospheres of these distant worlds. By studying the chemical composition of these exoplanet atmospheres, scientists aim to identify the building blocks of life and search for signs of habitability. The search for life on other planets is one of the most profound questions of modern science, and Webb holds the potential to provide the answers. Through Webb's extraordinary capabilities, we are on the cusp of a new era in space exploration, one where we can begin to answer age-old questions about our place in the universe and the possibility of life beyond Earth. The future of astronomical discovery is unfolding before our eyes, and with each technological advancement, we step closer to unraveling the deep mysteries of the cosmos. As humanity embarks on its journey deeper into the cosmos, the quest to answer fundamental questions about the universe's true nature intensifies. Among the most profound mysteries are the elusive concepts of dark matter, dark energy, and the ongoing expansion of the universe itself. These enigmas, which make up the unseen majority of our cosmos, challenge our understanding of the universe and its origins. The James Webb Space Telescope, JWST, with its cutting-edge technology, is poised to scrutinize these phenomena and unlock their secrets. By refining our understanding of these invisible forces, JWST has the potential to reveal the hidden processes that govern the very fabric of the universe, offering fresh insights that may push the boundaries of astrophysical thought. This telescope promises to illuminate the past, present, and future of our universe in ways that were once thought impossible. In recent years, advancements in computational power and simulation technology have significantly transformed our understanding of cosmic events. What was once pure speculation or theoretical abstraction can now be visualized and explored in highly detailed models that bring the universe to life. Scientists can now simulate everything from the earliest moments after the Big Bang, when the universe was just a hot, dense soup of particles, to the chaotic dance of galaxies as they collide and interact. These simulations are not merely academic exercises, they are vital tools that allow researchers to explore the unknown, test hypotheses, and gain insights into cosmic phenomena that would otherwise be impossible to observe directly. By modeling complex cosmic interactions under different conditions, researchers can begin to unravel the forces that shape the evolution and behavior of the universe. One of the most fascinating areas of study that benefits from these simulations is the study of black holes. These mysterious objects, once considered purely theoretical, are now better understood thanks to cutting-edge computational models. Through simulations, scientists have been able to predict how black holes form, grow, and interact with their surrounding environments. These models provide valuable insights into the behavior of supermassive black holes at the centers of galaxies, revealing how they influence the galaxies that surround them. Such research not only enhances our knowledge of black holes themselves, but also sheds light on the role these objects play in the broader cosmic ecosystem. In addition to black holes, these simulations also allow scientists to investigate other phenomena that are too distant or challenging to observe directly. For example, stellar explosions like supernovae are modeled in great detail, helping scientists understand the life cycle of stars and the creation of heavy elements in the universe. These simulations are crucial for explaining how elements such as carbon, oxygen, and iron, which are essential for life on Earth, were forged in the interiors of ancient stars. The study of these explosive events provides key insights into how the building blocks of planets and life came to be. As the power of computers continues to grow, so too does the precision and scale of these simulations. With the ability to simulate billions of stars and their interactions, researchers can model the universe in unprecedented detail. This ever-expanding computational capacity enables simulations to include more variables and run under more complex conditions, offering deeper insights into the structure of the universe and the laws of physics that govern it. As technology advances, these simulations will become increasingly refined, revealing new layers of understanding about the cosmos and challenging our assumptions about how the universe operates. In parallel, international collaboration in space exploration has emerged as a powerful force in advancing our collective knowledge of the universe. Space missions are incredibly costly, and by pooling resources, expertise, and technology from various countries, nations can launch more ambitious projects than they could manage alone. This collaborative spirit fosters not only cost-sharing, but also the exchange of ideas, with diverse teams bringing unique perspectives that can lead to innovative solutions to complex problems. One of the most notable examples of international collaboration is the International Space Station, ISS, a remarkable testament to human cooperation. By merging the talents and resources of multiple countries, the ISS has become a hub of scientific research, yielding discoveries that benefit all of humanity, from advances in medicine to breakthroughs in material science. However, international cooperation is not without its challenges. The complexity of coordinating large, multi-nation projects often involves navigating different political agendas, funding priorities, and bureaucratic hurdles. Each participating nation brings its own timeline, goals, and expectations, which can create friction and complicate coordination. At times, the interests of one country may not align with those of another, leading to delays or even the stalling of important initiatives. While such conflicts are part of any large-scale project, they must be carefully managed to ensure that collaboration remains productive and that scientific progress continues unimpeded. Nevertheless, despite these challenges, the benefits of international collaboration far outweigh the drawbacks. As space exploration becomes more complex and the demands of missions increase, the pooling of global resources and expertise is crucial to achieving scientific breakthroughs. Whether it's launching missions to distant planets, studying the mysteries of dark matter, or investigating the potential for life beyond Earth, international partnerships are vital to pushing the boundaries of human knowledge. In the end, it is through cooperation and shared effort that we will continue to unlock the vast mysteries of the universe, forever reshaping our understanding of the cosmos and our place within it. Technology transfer and intellectual property rights have always been contentious issues in international collaboration, and this holds true especially in the context of space exploration. Many nations, wary of sharing their most sensitive technologies, fear that these advancements could be used for military purposes or give their competitors a strategic edge. These concerns, however, do not stand in the way of the ever-growing drive for exploration. Humanity's curiosity about the cosmos and the mysteries it holds continues to foster collaboration between nations, even as technological and political barriers persist. As we reach beyond our planet, international cooperation remains a vital tool to confront some of the greatest challenges and unknowns that humanity faces. One of the most fascinating phenomena in the universe is the quasar, a short form of quasi-stellar object. These enigmatic celestial bodies are among the brightest and most distant objects we can observe. At their core, quasars are powered by supermassive black holes, which reside at the centers of galaxies. As matter from the surrounding environment spirals toward these black holes, it heats up to millions of degrees, emitting vast amounts of energy. This energy output is so intense that quasars can outshine entire galaxies, often becoming the most luminous objects in the universe. The immense brightness of quasars enables us to detect them even at incredibly great distances. Some quasars are located billions of light years away, which means that the light we observe from them has been traveling through space since the universe was still in its infancy, roughly 1 to 2 billion years after the Big Bang. This time lag gives scientists a unique opportunity. By observing quasars, we can peer back into the early stages of the universe's formation. In this way, quasars act as cosmic beacons, illuminating the conditions of the universe at a time long before the Earth or even our solar system came into existence. Their light reveals vital information about how galaxies formed and evolved. By analyzing the spectrum of light emitted by these distant objects, astronomers can study the composition of the early universe, including the types and densities of elements present at the time. These observations also provide insights into the intergalactic medium, the space between galaxies, and offer clues about the development of the first stars and galaxies. Each quasar we observe acts like a snapshot from the past, giving us an ever clearer picture of the universe's early history. Quasars are not just valuable for understanding the origins of galaxies, they also play a crucial role in studying the rate of cosmic expansion. The redshift observed in the light from quasars allows scientists to measure how quickly the universe has been stretching over time. This is a key piece of the puzzle in cosmology, offering confirmation of our models of the universe's expansion. Furthermore, these measurements lead to important questions about dark energy, the mysterious force driving the accelerating expansion of the universe. Thus, quasars function as both laboratories and time machines, enabling us to explore the past and expand our understanding of the future. Another mesmerizing natural phenomenon is the aurora, often referred to as nature's light show. These stunning light displays, which typically grace the skies near the Earth's magnetic poles, are the result of charged particles from the sun interacting with gases in Earth's atmosphere. The magnetic field of the Earth guides these particles toward the poles, where they enter the atmosphere and collide with oxygen and nitrogen atoms. As a result of these collisions, the atoms become excited and release energy in the form of light. The colors of the aurora vary depending on the type of gas involved and the altitude at which the collisions occur. Oxygen, for example, can produce green and red hues, while nitrogen contributes blues and purples. At higher altitudes, where nitrogen is more abundant, the aurora may appear in deep purple tones. In contrast, lower altitude interactions, where oxygen dominates, tend to produce the iconic green colors many people associate with the phenomenon. This vibrant and dynamic display is not only visually stunning, but also reveals the complex interaction between solar wind, Earth's magnetic field, and the atmosphere. The intensity of auroras is closely linked to solar activity, and during times of heightened solar storms, such as solar flares or coronal mass ejections, the auroras can be observed far beyond the polar regions, captivating onlookers in places where they are usually unseen. These displays serve as a reminder of the interconnectedness of our planet with the broader cosmos. The interplay of space weather, magnetic forces, and atmospheric conditions brings these breathtaking displays of light to life, offering us a glimpse into the intricate mechanisms of the universe. Finally, magnetars represent one of the most extreme types of neutron stars. Neutron stars are the remnants of massive stars that have exploded in supernovae, leaving behind a dense, compact core composed almost entirely of neutrons. Magnetars, however, are a subclass of neutron stars, distinguished by their extraordinary magnetic fields. While typical neutron stars have strong magnetic fields, magnetars possess magnetic fields so intense that they can reach up to 1 trillion Gauss, more than 1 million times stronger than the strongest magnetic field ever generated on Earth. These intense magnetic forces profoundly affect the surrounding space. The magnetic fields of magnetars are so powerful that they can distort the structure of nearby matter, influencing the behavior of surrounding gas and even emitting bursts of X-rays and gamma rays. The creation of a magnetar begins when a massive star runs out of nuclear fuel and undergoes a supernova explosion. The core of the star collapses under its own gravity, and the outer layers are ejected into space. This collapse leads to the formation of a neutron star, and under certain conditions, it can become a magnetar with an ultra-powerful magnetic field that defies all known laws of physics. These cosmic objects, though distant and elusive, are key to understanding the fundamental forces of the universe. As we continue to explore space, magnetars like quasars and auroras remind us of the extreme and awe-inspiring phenomena that govern the cosmos. They challenge our knowledge, pushing the boundaries of what we understand about matter, energy, and the forces that shape our universe. However, the conditions within a magnetar during its process of evolution amplify its magnetic energy, creating unique properties that set magnetars apart from other celestial objects. The magnetic fields in magnetars are unlike anything observed elsewhere in the universe, with strength levels that far surpass those of regular neutron stars. These intense magnetic forces can lead to catastrophic starquakes, violent seismic events that shake the core of the star. These disturbances are so powerful that they can trigger bursts of high-energy gamma rays, radiating out into space and making the magnetar observable from vast distances. In comparison, regular neutron stars, which are primarily characterized by their rapid rotation and associated pulsar activity, behave quite differently. While both types of stars are incredibly dense remnants of supernova explosions, magnetars rotate more slowly and emit less consistent radiation than pulsars. The key difference lies in their magnetic fields, which play a pivotal role in the emissions of these extraordinary stars. Bursts of gamma rays and X-rays can appear sporadically, often without warning, showcasing the erratic and unpredictable nature of the interactions between their immense magnetic fields and the surrounding space. Studying magnetars opens a window into some of the most extreme conditions found in the universe. These enigmatic celestial objects offer valuable insights into the nature of matter when subjected to intense pressure, as well as into the fundamental physics of magnetic fields. By delving into the study of magnetars, scientists continue to uncover the mysteries surrounding stellar life cycles and the forces that shape our cosmos. Each new discovery not only enhances our understanding of magnetars, but also invites deeper questions about the life cycles of stars and the conditions that govern their evolution. Cosmic rays, high-energy particles traveling through space at nearly the speed of light, play a crucial role in our understanding of both the universe and life on Earth. These particles originate from a variety of sources, including the Sun and distant supernova. Upon reaching Earth, they collide with atoms in our atmosphere, creating secondary particles that cascade down to the surface. Although many cosmic rays are absorbed by Earth's atmosphere or deflected by its magnetic field, some manage to penetrate deeper, reaching the surface and impacting the planet in subtle but significant ways. The effects of cosmic rays on life on Earth are profound, though often not immediately apparent. For one, cosmic rays contribute to the natural background radiation that all living organisms are exposed to. This radiation over time can lead to mutations in DNA, which may have both beneficial and harmful consequences for life. While some mutations may drive evolution, introducing new traits that species can adapt to, others can lead to genetic disorders, including cancer. Interestingly, studies suggest that cosmic rays may also play a role in cloud formation and even influence climate patterns. When cosmic rays collide with atmospheric molecules, they ionize them, potentially leading to the formation of cloud condensation nuclei. This process may alter weather and climate conditions by affecting the amount of sunlight reaching Earth's surface and influencing precipitation patterns. While the exact mechanisms of these effects are still being researched, this connection highlights the profound interconnectedness between the cosmos and Earth's atmosphere. Cosmic rays, far from being just particles zipping through space, exert a significant influence on life on Earth, affecting everything from genetic variation and evolution to the potential shaping of our climate. They serve as a reminder of the dynamic forces at play in both nature and the universe, illustrating the relationship between our planet and the vastness of space. Planetary alignments and eclipses have fascinated humanity for millennia, captivating our imagination and fueling curiosity about the cosmos. These celestial events, often viewed as symbols of harmony and order, have led to connections being drawn between the movements of the heavens and human affairs. In many cultures throughout history, eclipses were seen as omens, believed to carry messages from the gods, evoking awe and sometimes fear. In modern times, while the mystical interpretations have largely faded, eclipses and planetary alignments continue to inspire wonder, offering a chance for us to better understand the mechanics of our solar system. A planetary alignment occurs when several planets line up in a specific order in the sky. While these alignments don't carry the mystical powers some people may ascribe to them, they do provide a unique opportunity for scientists and astronomers to study the gravitational interactions and dynamics of celestial bodies. For amateur astronomers and enthusiasts, these alignments present an opportunity to witness the vastness of space firsthand, reminding us of the complexity and beauty of our cosmic neighborhood. Observing these events can feel like peering into the intricate dance of the universe, a reminder of our place in the ever-expanding cosmos. Eclipses, particularly solar and lunar eclipses, are profound spectacles that have the power to transform an ordinary day into an extraordinary moment of wonder. A solar eclipse, for example, occurs when the moon passes directly between the Earth and the sun, casting a shadow that momentarily blocks out the sun's light. This dramatic change in daylight can alter the atmosphere, creating a sense of awe among those who witness it. Crowds of spectators often gather to watch, and these shared experiences foster a sense of community, blending scientific fascination with cultural significance. Whether in ancient times, when eclipses were seen as messages from the gods, or today when they offer a window into the celestial mechanics of our solar system, eclipses continue to evoke a sense of wonder. These events remind us of the beauty and complexity of our universe and of the ever-present connections between the movements of the stars and our lives on Earth. Eclipses, in all their awe-inspiring mystery, have long played a pivotal role in the history of science, serving as extraordinary moments that not only capture the public's imagination, but also propel humanity toward new frontiers of knowledge. One of the most significant of these was the total solar eclipse of 1919, an event that became a critical turning point in our understanding of the universe. It was during this eclipse that experimental confirmation was provided for Albert Einstein's groundbreaking theory of general relativity, forever altering the trajectory of physics. As light from distant stars passed close to the sun, it bent around the massive object, just as Einstein had predicted, proving that light is not simply a straight-line phenomenon, but a curve influenced by gravity. This was more than just a confirmation of a scientific theory. It was a defining moment that bridged the gap between abstract mathematical ideas and the tangible world, pushing us toward a deeper comprehension of the cosmos. From ancient civilizations who saw eclipses as divine omens, to modern-day physicists using them as tools to test the fabric of space and time, eclipses have always been more than just astronomical events. They represent the intersection of imagination and scientific inquiry, fueling our desire to explore the universe's deepest mysteries. Whether viewed through the eyes of ancient astronomers or contemporary scientists, these celestial occurrences are not just physical phenomena, but also symbols of humanity's eternal quest for knowledge. The lessons they teach us are as profound as they are timeless. At the heart of modern physics lies Albert Einstein's theory of relativity, a revolutionary framework that redefined how we think about space, time, and gravity. Einstein's theory is composed of two key components: special relativity and general relativity. Special relativity upended classical ideas of space and time, asserting that the laws of physics are the same for all observers, regardless of how fast they are moving. This led to the radical realization that the speed of light is a constant, an unchanging, universal speed that is the same for all observers, regardless of their motion relative to the light source. This insight also brought with it a profound consequence. Space and time are not separate entities, but are instead interwoven into a single continuum known as space-time. Time itself, Einstein showed, is not fixed. It can stretch or contract depending on the speed at which an object is moving, a concept that seems almost unimaginable yet has been confirmed through countless experiments. Building on this, general relativity expanded on these ideas, introducing a new way of understanding gravity. In the framework of classical mechanics, gravity was understood as a force, one that attracted masses toward each other. Einstein, however, proposed that gravity is not a force at all, but a curvature in the fabric of space-time itself. Imagine space-time as a vast, flexible sheet. When a massive object, like a planet or a star, sits on this sheet, it causes a depression, pulling smaller objects toward it. This concept allows us to understand phenomena like the orbits of planets and the bending of light around massive objects, a phenomenon known as gravitational lensing. This new understanding of gravity as the geometry of spacetime offers a deeper and more complex relationship between mass, space, and time. Rather than simply pulling objects together, gravity is the manifestation of spacetime bending around massive objects. The implications of this insight are enormous. Not only does it change how we understand the motion of planets and stars, but it also gives us the tools to explore some of the most mysterious and extreme environments in the universe, such as black holes. These are regions where space-time curvature becomes so intense that not even light can escape. The detection of gravitational waves, ripples in space-time caused by accelerating masses, has provided direct evidence supporting these ideas, allowing us to observe phenomena that were once thought to be beyond our reach. Einstein's theories also transformed our understanding of the cosmos on a grand scale. The concept of an expanding universe, as first proposed by Edwin Hubble, finds its roots in general relativity. This expansion, Einstein's equations suggest, is not simply the movement of galaxies through space. Rather, it is space itself stretching, expanding the very fabric of the universe. This dynamic nature of space and time implies that the universe is not a static entity, but a living, evolving one, where time and distance are not immutable, but can stretch, bend, and contract. This realization places human existence into a broader cosmic context, where the dimensions of time and space are not fixed but adaptable, influenced by the very structure of the universe. The effects of Einstein's theories permeate all areas of modern physics. From the study of black holes to the detection of gravitational waves, relativity remains foundational to our understanding of the universe. It also plays a crucial role in cosmology, particularly in our exploration of the Big Bang and the subsequent evolution of the universe. As scientists continue to probe the cosmos, the theory of relativity remains a powerful tool for understanding the large-scale structure of the universe, from the behavior of galaxies to the overall shape and destiny of the cosmos itself. However, the world of physics is not confined to the macroscopic realm alone. The universe at its smallest scale, the realm of quantum mechanics, reveals a different set of rules entirely. While classical cosmology, grounded in the work of figures like Newton and Einstein, offers a framework for understanding the large-scale behavior of the universe, quantum mechanics delves into the strange and often counterintuitive behavior of particles at the atomic and subatomic levels. At these scales, particles do not follow predictable paths. Instead, they exhibit behaviors that are defined by uncertainty, superposition, and entanglement, phenomena that seem to defy common sense. This divergence between classical and quantum physics becomes especially apparent when studying extreme environments such as black holes, where both quantum effects and gravitational influences are significant. The challenge facing modern physics is to reconcile these two seemingly contradictory realms. Classical theories of gravity rely on smooth space-time constructs, while quantum mechanics suggests that, at the smallest scales, the very fabric of reality is chaotic and unpredictable. One of the key questions arising from this clash of paradigms is the issue of information retention in black holes. According to classical physics, any information that enters a black hole is lost forever. But quantum mechanics suggests that information cannot be destroyed, leading to the so-called information paradox. Resolving this paradox is one of the most pressing challenges in modern theoretical physics, and researchers are exploring ideas like quantum gravity in an attempt to unify these two divergent frameworks. This quest for unification has led to the development of exciting new theories, such as string theory, which aims to provide a single, unified framework for understanding all fundamental forces and particles in the universe. In contrast to the classical view of particles as point-like objects, string theory proposes that the most basic constituents of the universe are tiny, vibrating strings. These strings can oscillate in different ways, and the pattern of their vibrations determines the properties of the particles they form, such as mass and charge. One of the most exciting implications of string theory is its potential to unify gravity with the other fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. In traditional physics, gravity has always been treated as a separate force, governed by Einstein's theory of general relativity, while the other three forces are described by quantum mechanics. String theory, however, acts as a bridge between these two realms, offering the possibility of a single, unified theory of everything, a deeper framework that could govern the fabric of our universe at every scale. The pursuit of such a unified theory promises to reshape our understanding of the cosmos in profound ways. If string theory is correct, it could provide answers to some of the most fundamental questions about the nature of space, time, and matter. More importantly, it might unveil a deeper level of reality, one that transcends our current understanding of the universe. As we continue to explore these questions, one thing is certain: the journey of discovery is far from over. The universe in all its complexity continues to challenge our minds, and with each new breakthrough, we take one step closer to understanding the profound mysteries that lie beneath the surface of existence itself. String theory goes beyond the conventional understanding of reality, proposing that the universe is not confined to the four dimensions we experience daily. Most of us are familiar with three dimensions of space: length, width, and height, and one dimension of time, which together shape our daily interactions with the world around us. However, string theory suggests there could be as many as 10 or 11 dimensions, far beyond the scope of human perception. These extra dimensions, though critical to the structure of the universe, are often described as compacted or curled up in such a way that they are invisible to the naked eye. They exist at scales so small that current technology cannot detect them directly. The true power of string theory lies in its implications. According to this theory, these hidden dimensions are not merely abstract concepts. They actually influence the fundamental forces and particles that shape the universe. These Extra dimensions act as the underlying framework, the very canvas on which the universe's physics are painted. Yet, despite its potential to revolutionize our understanding of the cosmos, string theory remains a largely untested and theoretical framework. The primary challenge is the incredibly tiny scale at which strings, the fundamental building blocks of matter, are believed to exist. The scale is so small, on the order of the Planck length, that it falls beyond the reach of current experimental technology. However, this doesn't mean that string theory is relegated to the realm of mere speculation. As scientists continue to explore and refine the concepts behind it, string theory presents a tantalizing glimpse of a more profound and elegant understanding of the universe. It suggests that the apparent complexity of nature, with all its myriad forces and particles, could arise from simple and harmonious principles that remain just beyond our grasp. The pursuit of these deeper truths continues to inspire ongoing research and fuels the collective curiosity about the fundamental nature of reality itself. This quest for unity in physics, for a theory that could unify all the forces of nature, motivates scientists to push the boundaries of what we know. Theoretical models, in many ways, serve as essential tools in this ongoing exploration of the universe. These models are not just abstract exercises. They represent sophisticated simulations of real-world physical systems, guided by the fundamental principles and laws that govern the natural world. They allow researchers to hypothesize about systems and phenomena that are either too distant or too microscopic to be directly observed. In doing so, these models provide critical insight into the workings of the universe, often in ways that traditional observation cannot. One of the most notable applications of theoretical modeling is in the study of celestial objects like black holes. Although black holes themselves cannot be directly observed, due to their incredibly dense nature and the fact that nothing, not even light, can escape their gravitational pull, their presence can be inferred from their influence on surrounding matter. Models built on our understanding of general relativity and quantum mechanics allow scientists to predict the behavior of black holes, including how they interact with nearby stars and gas clouds. These models can help us understand the phenomena that would otherwise be beyond our observational reach. The power of a theoretical model lies in its ability to make predictions. Once a model is developed, it can be used to forecast how a system will behave under specific conditions. These predictions are the very essence of scientific inquiry, as they guide researchers in designing new experiments and observational strategies. One of the most famous historical examples of this predictive power comes from the discovery of Neptune. In the 19th century, astronomers noticed unexplained discrepancies in the orbit of Uranus. Using mathematical models, they predicted the existence of an additional planet beyond Uranus, a planet that was later discovered and confirmed to be Neptune. Even after a model has been tested and predictions confirmed, the work is far from finished. As new data and observations come in, models are continually refined and adjusted. This iterative process ensures that the models remain accurate and relevant, adapting to the evolving understanding of the universe. It is this dynamic aspect of theoretical modeling, its constant evolution in response to new findings, that makes it such a crucial tool for advancing science. Whether it's explaining the formation of galaxies or predicting climate change patterns, the ability to forecast future outcomes based on current models provides scientists with a powerful lens through which to study the world. Ultimately, theoretical models are more than just tools for understanding the present. They are catalysts for further discovery. Each new prediction made by a model opens up new avenues for investigation, encouraging scientists to test new hypotheses and explore previously uncharted territory. They act as a bridge between established knowledge and the vast unknown reaches of scientific inquiry. With every breakthrough, these models help illuminate the path to answers that lie just beyond the horizon of our current understanding. One of the most intriguing and mind-bending ideas in modern theoretical physics is the concept of the multiverse. This theory proposes that the universe we live in is not the only one in existence. Instead, our universe is just one of a potentially infinite number of universes, each existing in a vast multiverse. These other universes may have entirely different physical laws, constants, and even dimensions of space and time. What this suggests is that the reality we experience might just be one of an endless variety of possibilities. Each universe could harbor its own unique set of phenomena, offering different experiences and structures of reality. The idea of the multiverse challenges many of the assumptions that underlie our traditional understanding of the cosmos. It pushes the boundaries of what we consider to be reality, suggesting that what we perceive as the universe is only a small fragment of a much larger, much more complex whole. The multiverse theory draws support from several fields of physics, particularly quantum mechanics. One interpretation of quantum mechanics, known as the many worlds interpretation, posits that every quantum event leads to the creation of multiple parallel universes. In this framework, every time a quantum decision is made, such as the flip of a coin, our universe splits into multiple branches, each corresponding to a different outcome. In one universe, the coin lands heads, in another it lands tails. While the concept of parallel universes is undeniably fascinating, direct evidence for their existence remains elusive. This lack of empirical confirmation has led to heated debates among physicists, with many questioning the feasibility of the multiverse theory. Yet, the theory is not without its supporters, and some aspects of it are even indirectly supported by other areas of physics. For example, the phenomenon of cosmic inflation, the rapid expansion of space during the early moments of the universe, provides further credence to the idea of a multiverse. According to this theory, different regions of space may have experienced inflation at different rates, leading to the formation of bubble universes. These bubbles could each develop their own set of physical properties, possibly leading to universes with entirely different laws of physics. Moreover, certain features of cosmic background radiation, tiny fluctuations in the energy left over from the Big Bang, may offer indirect evidence of interactions between these bubble universes. While this is still a topic of active research, it provides a tantalizing hint that the multiverse, though hidden from direct observation, may yet be real. The search for evidence of other universes continues, fueling both scientific inquiry and our innate curiosity about the ultimate nature of reality. Lastly, string theory, a framework that seeks to unify all fundamental forces of nature, often leads to intriguing predictions about the existence of a multiverse. This theory, with its multiple ways of compacting extra dimensions, suggests that there could be a vast number of possible configurations in the fabric of reality. As our understanding of these concepts deepens, the idea of a multiverse gains more traction, captivating both scientists and non-scientists alike. It prompts us to question the very nature of existence and wonder about the countless universes that could exist beyond the one we inhabit. Could other dimensions hold alternate versions of ourselves, or even entirely different laws of physics? The concept of the multiverse fuels imagination, pushing the boundaries of what we consider possible in the realm of modern physics. As scientists continue to explore string theory's complexities, the possibility that our universe is merely one of many in a vast, cosmic web grows ever more plausible. This revelation does not just spark curiosity, it challenges our perceptions of space, time, and the nature of reality itself. Wormholes are another fascinating product of theoretical physics that arise from Einstein's equations of general relativity. These hypothetical structures are imagined as shortcuts through the fabric of space-time, linking distant points in the cosmos, much like tunnels through the very fabric of the universe. If they were to exist, wormholes could theoretically allow for instantaneous travel between two far-flung regions of space, bypassing the time and distance that normally separates them. Although wormholes remain speculative at best, their implications challenge our understanding of the very nature of space and time. They present a compelling area of study for physicists, offering new avenues to explore the fundamental principles of the cosmos. However, one of the most intriguing aspects of wormholes is their potential for time travel. Imagine, if you will, a wormhole that connects 2 points not just in space, but in time, allowing a traveler to journey into the past or the future. Some physicists believe that traversable wormholes, stable enough to allow objects to pass through them, could theoretically exist. However, to keep such a structure open, a form of exotic matter with negative energy density would be required, something that has never been observed in nature. The idea of such exotic matter remains a speculative and elusive concept in modern physics. Still, these ideas capture our imagination, leading to profound questions about the nature of time and causality. As we delve deeper into the concept of time travel through wormholes, several paradoxes emerge. One of the most famous of these is the grandfather paradox. This thought experiment asks what would happen if someone were to travel back in time and prevent their grandfather from meeting their grandmother. Would they ever exist to make that journey in the first place? Such paradoxes reveal the intricate and often perplexing relationship between time and cause and effect, complicating our understanding of temporal travel. Despite the lack of concrete experimental evidence or methods to create or manipulate wormholes, these theoretical constructs continue to be a central topic in modern physics. Their speculative nature serves as a bridge, pushing us to the limits of our scientific knowledge and encouraging further exploration into the mysteries of the universe. As we continue to study the cosmos and the laws of physics, wormholes serve as a reminder of the infinite possibilities that lie just beyond our current understanding. They fuel our curiosity and inspire new lines of inquiry, challenging our perceptions of reality and opening the door to realms that remain beyond our reach. The Apollo moon missions, conducted by NASA from the late 1960s to the early 1970s, stand as one of the most extraordinary achievements in human history. The most iconic of these missions, Apollo 11, made history on July 20th, 1969, when astronauts Neil Armstrong and Buzz Aldrin became the first humans to walk on the lunar surface. This momentous event not only fulfilled President John F. Kennedy's bold promise to land a man on the moon by the end of the decade, but it also symbolized the triumph of human ingenuity, ambition, and determination during the intense competition of the space race. Beyond merely landing on the moon, the Apollo missions made significant contributions to science and technology. Over the course of 6 successful lunar landings, astronauts collected nearly 800 pounds of lunar rocks and soil. These samples, brought back to Earth, have provided invaluable insights into the moon's geological history and composition. Scientists discovered that the moon is approximately 4.5 billion years old, a similar age to that of Earth. This discovery led to the development of theories about the formation of both the moon and our planet, which likely emerged from a primordial disk of gas and dust around the young sun. The Apollo program also had far-reaching impacts on technology and engineering. The innovations developed to support these missions led to advancements in a wide range of fields, including material science, computer technology, and life sciences. For instance, the miniaturization of computing systems necessary for the reliability of guidance and navigation systems paved the way for the powerful, compact computers that we use today. Furthermore, the medical and life sciences research conducted during these missions deepened our understanding of how the human body responds to the extreme conditions of long-duration space travel, providing crucial knowledge for future exploration beyond Earth. In addition to its scientific achievements, the Apollo program fostered international collaboration and inspired countless individuals around the world. The missions demonstrated what humanity can achieve when driven by curiosity, dedication, and a shared sense of purpose. Today, the legacy of the Apollo missions continues to resonate, influencing ongoing missions to explore not just the moon, but Mars and beyond. The story of Apollo stands as a testament to humanity's boundless potential and our desire to explore the farthest reaches of the cosmos. The Voyager missions, launched in the late 1970s, marked another milestone in humanity's journey of exploration, this time venturing into the distant outer reaches of our solar system. Voyager 1 and Voyager 2, both equipped with advanced instruments and cameras, provided humanity's first close-up views of the giant planets and their moons. The data and images returned by these spacecraft significantly expanded our knowledge of the outer solar system, revealing details about distant worlds that were once only visible through telescopes from Earth. Voyager 2, in particular, stands out as the only spacecraft to have visited Uranus and Neptune up close. This mission provided crucial data about these ice giants, revealing their unique atmospheres, magnetic fields, and faint rings. Before the Voyager missions, these distant planets were largely shrouded in mystery, their characteristics only theorized. The wealth of data sent back by Voyager 2 transformed our understanding of these far-off worlds, including new insights into the complex dynamics of their moons. One of the most significant discoveries made by Voyager 2 was the geological activity observed on Triton, Neptune's largest moon. This icy moon was found to have geysers spouting nitrogen gas, suggesting the presence of a subsurface ocean beneath its frozen surface. This discovery opened up new possibilities for understanding the potential for life in the outer solar system and deepened our fascination with the mysteries of distant moons and planets. As the Voyager spacecraft continue their journey into interstellar space, they represent the unyielding spirit of human exploration, relentlessly pushing the boundaries of what we know about our solar system and beyond. These missions, like the Apollo program before them, inspired generations of scientists, engineers, and explorers to continue reaching for the stars. The Voyager missions, launched in the late century, marked a pivotal moment in humanity's exploration of the cosmos. As these spacecraft journeyed deeper into the vastness of space, they captured stunning revelations about our solar system and beyond. Among their many accomplishments, the Voyagers discovered several new moons orbiting the gas giants Jupiter and Saturn, significantly expanding our understanding of the diverse range of celestial bodies that populate our corner of the universe. Yet the Voyagers' most profound contribution came when they ventured into interstellar space. By pushing past the outermost reaches of the solar system, they sent back a final, invaluable transmission offering a wealth of data about the heliosphere. This invisible bubble, created by the solar wind, extends far beyond the orbits of the farthest planets, shielding our solar system from the harsh interstellar medium. The data transmitted by the Voyagers has given scientists a clearer picture of the boundary between our solar system and the space beyond, shedding light on how the solar wind interacts with the surrounding interstellar environment. Even today, decades after their launch, the Voyager spacecraft continue to communicate with Earth, offering us a continuous thread to the past, present, and future of space exploration. These ongoing transmissions remind us that the journey of discovery is far from over. Exploration does not just expand our knowledge, it fuels our sense of wonder and connects us to the vast, mysterious universe beyond our planet. As we continue to reach further into the cosmos, our missions to Mars have become some of the most ambitious and scientifically rich endeavors of our time. Driven by a combination of scientific curiosity, the desire for human exploration, and the quest to uncover potential life beyond Earth, these missions aim to reveal the mysteries of the Red Planet. Among the foremost goals is to understand Mars's geology and climate. By studying the surface rocks, soil, and atmosphere, scientists hope to uncover clues about Mars's past. Learning how its environment evolved over billions of years could provide insights into the processes of planetary development, including those that shaped our own Earth. Equally important is the search for signs of life, both past and present. Mars, in its ancient history, likely had conditions that could have supported life, conditions such as liquid water and a thicker atmosphere. Rovers like Perseverance, equipped with state-of-the-art instruments, are tirelessly analyzing rock samples and searching for organic compounds, which could provide the first concrete evidence of extraterrestrial life. Such a discovery would not only revolutionize our understanding of biology, but also redefine humanity's place in the vast universe. Mars exploration, however, is about more than just scientific discovery. It serves as a crucial stepping stone for the future of human space exploration. NASA's Artemis program, which focuses on returning astronauts to the moon, is closely tied to the exploration of Mars. The lessons learned from these lunar missions will play a critical role in preparing for the human colonization of Mars. Key challenges, such as understanding radiation exposure, developing life support systems, and mastering in-situ resource utilization, must be addressed if humanity is to survive and thrive on Mars during long-duration missions. As Mars continues to captivate the imaginations of scientists and the public alike, the push for exploration emphasizes humanity's enduring drive to explore the unknown, to discover new worlds, and to connect with the cosmos. This quest is not merely about satisfying curiosity. It represents our determination to push the boundaries of knowledge, to reach beyond the familiar, and to prepare for the future voyages that may take us even further into the depths of space. At the same time, initiatives like the International Space Station, ISS, stand as vital pillars of modern space exploration. The ISS, which orbits Earth and serves as an international research laboratory, is a remarkable symbol of global cooperation. Launched in the late 20th century, the ISS is the product of a unique partnership between countries including the United States, Russia, Europe, Japan, and Canada. This collaboration has led to groundbreaking scientific advancements across numerous disciplines, from biology to material science, providing valuable insights into how life functions in space. One of the ISS's most significant features is its microgravity environment. This near weightlessness provides a unique setting for conducting experiments that would be impossible or far less effective on Earth. In this altered state of gravity, researchers are able to observe phenomena such as fluid dynamics, combustion processes, and biological behavior in entirely new ways. For instance, studying how cells grow and react to stimuli in microgravity has already yielded promising breakthroughs in medical treatments, offering new avenues for understanding human health. Moreover, the ISS plays a crucial role in fostering international cooperation, allowing scientists from diverse countries to work side by side, sharing expertise and resources. This spirit of collaboration enhances the quality of the research conducted and strengthens diplomatic ties between nations, contributing to a sense of global unity. Through joint missions, experiments, and educational outreach programs, the ISS serves not only as a hub for scientific progress, but as an inspiration for future generations, emphasizing the power of teamwork in the pursuit of knowledge. In this way, both the Voyager missions and the ongoing space endeavors, such as Mars exploration and the International Space Station, embody humanity's endless curiosity and resolve. They represent our ceaseless search for answers to the most profound questions about life, the universe, and our place within it. These missions remind us that no matter how far we venture into the cosmos, the pursuit of knowledge and understanding is a journey that unites us all. The data collected from experiments conducted aboard the space station is an invaluable treasure trove that continuously feeds back into the global scientific community, sparking progress across diverse fields. This data plays a pivotal role, influencing advancements ranging from the development of more effective vaccines to the optimization of agricultural practices under extreme conditions. The knowledge gained from space resonates deeply across Earth's scientific pursuits, enhancing our understanding of fundamental processes and helping us tackle problems with far-reaching implications. At its core, the International Space Station, ISS, is far more than just a group of interconnected modules floating in orbit. It stands as a symbol of human ingenuity and international cooperation, showcasing our collective determination to answer some of the most profound questions of science and beyond. It represents humanity's shared aspirations to understand not only our own planet, but also the farthest reaches of space, pushing the boundaries of what is possible. Looking toward the future, the dream of establishing human settlements on the Moon and Mars fills many with a sense of wonder and excitement, yet it also presents an array of complex and formidable challenges. These challenges stem largely from the harsh and inhospitable environments on both celestial bodies. The Moon, for example, is subject to extreme temperature fluctuations, with daytime highs soaring to nearly 100 degrees Celsius and nighttime lows plunging to 150 degrees Celsius. Mars, on the other hand, offers a somewhat more temperate environment, yet it remains bitterly cold, with average temperatures hovering around minus 60 degrees Celsius. These extremes demand that any human habitats built on either body be able to endure these temperature variations, providing both insulation against the cold and protection from the harsh radiation that bombards their surfaces. Another significant hurdle lies in the scarcity of essential resources on both the Moon and Mars. Water and air, crucial for human survival, are in short supply. However, recent studies have discovered evidence of water ice on the moon, especially in craters that remain permanently shadowed. While this discovery offers hope, the challenge remains. How can we extract and use this water in a way that is both sustainable and efficient? Similarly, Mars has been found to harbor water in the form of ice, but converting this ice into liquid water suitable for drinking or agriculture is an engineering problem that must be solved. Relying on Earth for a steady supply of resources would be prohibitively expensive and logistically difficult, making the ability to utilize local resources, known as in situ resource utilization, critical for any long-term human presence on these distant worlds. Despite these obstacles, the potential rewards of human settlement are nothing short of thrilling. The Moon, with its proximity to Earth, could act as a vital springboard for deeper space exploration. Its closer orbit allows for faster travel, which could make it an ideal site for research stations. These stations could serve as experimental grounds for the technologies needed to establish a human presence on Mars, testing everything from life support systems to habitat construction. Moreover, the Moon's surface is rich in helium-3, a rare isotope that could one day serve as a fuel source for nuclear fusion, providing a virtually limitless supply of clean energy. Within a decade or two, these developments could form the foundation for sustainable human habitation beyond Earth. Mars, with its striking geological features and Earth-like day-night cycle, offers an even more tantalizing prospect. The Martian day is almost the same length as an Earth day, lasting just shy of 24 hours, and its diverse landscape includes towering mountains, vast valleys, and even the largest volcano in the solar system. Scientists are exploring the possibility of terraforming Mars, altering its atmosphere to make it more hospitable to life. While this concept remains theoretical, it is an idea that captivates the imagination and has driven significant research into how we might create conditions suitable for agriculture and human habitation. As technology advances, the dream of becoming a multi-planetary species grows ever closer, inching towards the realm of possibility. Meanwhile, satellite technology has revolutionized the way we connect, communicate, and observe the world around us. Since the launch of the first satellites in the mid-20th century, this technology has expanded rapidly, enabling the transmission of information across vast distances at incredible speeds. From providing television broadcasts to ensuring global internet connectivity, satellites have bridged geographical gaps and brought people closer together than ever before. But their impact goes far beyond communication. They also play an essential role in monitoring Earth's environment. Earth-observing satellites gather critical data on weather patterns, natural disasters, and the ongoing effects of climate change. This information is vital for scientists and meteorologists, allowing them to track storms, monitor deforestation, and even predict agricultural yields. Satellite technology has become a cornerstone of climate science, underpinning both short-term weather forecasting and long-term studies that are crucial to addressing the global environmental challenges we face. In addition, the development of Global Positioning System, GPS satellites, has transformed the way we navigate the world. Whether it's guiding a car on a road trip or ensuring precise timing for operations in industries like shipping or finance, GPS technology has become an indispensable part of daily life. Looking ahead, the future of satellite technology is poised for even greater advancements. The miniaturization of satellite components has led to the rise of small satellites, often referred to as CubeSats. These compact devices are opening up new avenues for research and commercial applications, enabling more frequent and cost-effective access to space. Furthermore, satellite constellations, which consist of multiple satellites working together, promise to significantly improve global connectivity, particularly in remote regions where traditional infrastructure is lacking. As satellite technology continues to evolve, our ability to monitor and protect our planet will only improve, helping us navigate the complex challenges of the present and future. Beyond Earth, asteroid mining is emerging as a promising frontier with vast potential for both economic and environmental benefits. As the planet's natural resources dwindle, asteroids rich in metals and minerals present an enticing alternative. These celestial bodies contain vast quantities of valuable materials, including platinum, gold, and rare earth elements, By tapping into this extraterrestrial resource, we could reduce the strain on Earth's ecosystems, mitigating the need for environmentally destructive mining practices. Instead of ravaging landscapes and destroying habitats, we could extract essential materials directly from space. Economically, asteroid mining holds the potential for substantial financial returns. The market for metals and minerals is immense, and the sheer abundance of these resources in some asteroids could drive down prices, benefiting industries from electronics to renewable energy technologies. In this way, asteroid mining could help to meet the growing demand for critical materials while simultaneously alleviating pressure on Earth's environment. As technology advances and our understanding of space exploration deepens, asteroid mining may one day become a cornerstone of a sustainable spacefaring future. Asteroid mining, an emerging frontier in space exploration, holds vast potential not only for scientific discovery but also for revolutionizing the economy and advancing technology. With the growth of this new space economy, an endless array of opportunities could arise, ranging from mining resource transportation to cutting-edge research. The innovative breakthroughs driven by this industry could ignite advancements in technology and engineering that we can hardly imagine today. Yet asteroid mining is not simply about extracting valuable materials. It represents a pivotal step in humanity's broader aspirations to venture deeper into space. The logistics involved in extracting and processing materials from asteroids could lay the foundation for humanity's long-term presence on celestial bodies beyond our own planet. This monumental achievement could serve as a launch pad for missions to Mars, the moons of Jupiter, and even further, helping to transform ambitious goals into reality. By utilizing resources found in space, such as water and metals, we could drastically reduce the astronomical costs of transporting goods from Earth. This would make otherwise impossible space missions, like colonizing other planets, much more feasible. Moreover, establishing a robust asteroid mining industry could foster unprecedented international cooperation in space exploration. Nations from across the globe would be compelled to work together, aligning their efforts on regulations, technological development, and common interests. This spirit of collaboration would not only advance space science, but could also contribute to peace on Earth. When countries unite in the pursuit of a sustainable future for both space and planet Earth, the potential for global scientific achievement is limitless. In essence, the environmental and economic advantages of asteroid mining have the power to usher in a new era of responsible resource management, propelling humanity into a future where we no longer solely rely on Earth's finite resources, but instead look to the cosmos for the materials that will fuel the next great leaps in science and civilization. Meteoroids, small celestial bodies that travel through space, offer a rich, untapped source of knowledge about the history of our planet and the solar system at large. As these objects hurtle through space, they can provide critical clues to understanding the origins of Earth. When meteoroids enter Earth's atmosphere, they often disintegrate and become meteors. However, if they survive the fiery descent, they reach the surface as meteorites. These meteorites, once collected, become invaluable to scientists studying the early days of our planet. Meteorites are like ancient time capsules, preserving materials and conditions that date back to the formation of the solar system over 4.5 billion years ago. Many contain minerals that have remained unchanged since their formation, offering scientists a rare and direct look into the processes that led to the creation of Earth and other celestial bodies. The composition of meteorites is often a snapshot of the raw materials that were present in the early solar system, making them crucial for understanding the building blocks of planets. In addition to offering insights into the formation of the solar system, meteorites can reveal vital clues about Earth's early atmospheric conditions. Some contain tiny bubbles of gas that were trapped at the time of their formation, giving us a glimpse into the environment of early Earth. These tiny pockets of gas can help scientists understand the nature of Earth's primitive atmosphere and how it evolved to support life. Meteorites can also shed light on significant geological events in Earth's history. Studies of meteorite impacts show that large celestial bodies have collided with our planet throughout its history, sometimes with catastrophic results. The most famous of these impacts, the one that is thought to have caused the extinction of the dinosaurs around 66 million years ago, dramatically altered Earth's ecosystems. By studying these impacts, scientists can better understand how such catastrophic events shaped the planet's geological history and, by extension, the evolution of life itself. Ultimately, the study of meteoroids and meteorites is not just about looking back into Earth's past. It is about deciphering the long and often violent history that has shaped our present and will continue to influence our future. Each meteorite holds a story of the universe, of time, and of forces beyond our comprehension. As we continue to study these celestial visitors, we are uncovering secrets that will help us understand where we come from, where we are, and where we might be headed. In parallel with the scientific revelations gleaned from meteorites, the realm of space exploration has been significantly transformed by the unique research opportunities provided by microgravity environments. Experiments conducted in space, where gravity does not affect biological processes in the same way it does on Earth, have revolutionized our understanding of numerous medical phenomena. One of the most important discoveries facilitated by microgravity research is the behavior of proteins. In space, proteins tend to crystallize in more uniform structures than they do under the influence of gravity. This is a crucial breakthrough, as studying the crystals formed by proteins helps scientists understand their structure. This, in turn, opens the door to the development of new drugs and therapies that could treat previously untreatable diseases. Additionally, microgravity provides an exceptional opportunity to study disease mechanisms. For instance, scientists have been able to grow cancer cells in space, observing how these cells behave in conditions that are vastly different from those on Earth. This has revealed crucial insights into the behavior of cancer cells and opened up new pathways for treatment that were previously inaccessible. Understanding how cancer cells grow and react in microgravity may lead to the creation of targeted therapies with fewer side effects, improving the quality of treatment for patients. Another area of medical research that has benefited from microgravity studies is tissue engineering. By studying biological systems in space, scientists have been able to create three-dimensional tissue constructs that more accurately mimic the human body's biological processes. This breakthrough could eventually lead to the development of lab-grown tissues that could be used for transplants, reducing the need for donor organs or for testing the efficacy of new drugs without relying on human or animal subjects. In conclusion, the study of space phenomena, whether through asteroid mining, meteorite analysis, or research in microgravity, is a window into the future of both science and civilization. Each discovery not only deepens our understanding of the universe, but also provides the tools to transform life on Earth. As humanity continues to explore the cosmos, the boundaries of what we can achieve will expand in ways we have only begun to imagine. Understanding the effects of microgravity on the human body provides invaluable insights into the health challenges astronauts face during extended space missions. Microgravity, the near weightless environment of space, influences numerous biological processes, making it a critical area of study for space agencies worldwide. Researchers have primarily focused on muscle atrophy, bone density loss, and changes in the immune system, three major health risks that astronauts encounter during long-term space travel. When the body is exposed to microgravity, muscles that are not actively used for movement weaken and shrink, leading to a condition known as muscle atrophy. The lack of gravitational pull also causes bones to lose their density, making them more fragile. Additionally, the immune system experiences significant alterations, which could leave astronauts more vulnerable to infections and illnesses. By studying these changes, scientists are not only working to protect astronauts on their missions, but are also gaining insights that could revolutionize the way we understand aging and disease processes here on Earth. As we venture further into the cosmos, the medical discoveries we make through microgravity experiments will undoubtedly have profound implications for improving healthcare systems at home, offering new perspectives on the ways our bodies function and age. One of the most captivating phenomena in modern astrophysics is the discovery of fast radio bursts, FRBs. First identified in 2007, these incredibly brief yet powerful pulses of radio waves have intrigued scientists and sparked intense debate. Lasting only milliseconds, these bursts pack an energy punch equivalent to what the sun produces over several days. Despite their brief duration, FRBs are highly directional, originating from vast distances, billions of light years away. Their enigmatic nature makes them even more puzzling, as it seems unlikely that such enormous amounts of energy could be released in such a short time. The mystery of FRBs has given rise to numerous theories regarding their origin. Some bursts have been traced back to distant galaxies, but others remain unexplained, leading to heated discussions about their sources. One hypothesis is that they may be emitted by highly magnetized neutron stars known as magnetars. Another more speculative theory suggests that they could be signals from extraterrestrial civilizations, sparking excitement and curiosity about the possibility of intelligent life beyond Earth. This diversity of theories has only deepened the allure of FRBs as they challenge existing astrophysical models and invite new ones. Additionally, some FRBs have been observed to repeat at regular intervals, suggesting that there may be underlying processes or environmental factors that govern their emission. This repetition offers a tantalizing clue that could help researchers pinpoint their origin. On the other hand, non-repeating FRBs challenge scientists to rethink our understanding of cosmic phenomena and force a reevaluation of the models that have long dominated our views of the universe. The study of these bursts extends beyond answering fundamental questions. It also provides a unique opportunity to learn about the cosmic medium through which these signals travel. By analyzing FRBs, scientists gain valuable insights into the structures of the universe, magnetic fields, and even the expansion of space itself. Each new discovery adds another layer of mystery to the universe, propelling astronomers and astrophysicists to peer deeper into the cosmos, searching for answers that lie hidden in the stars. The Fermi paradox, named after physicist Enrico Fermi, presents a perplexing question about the existence of extraterrestrial life. With the vast number of stars and potentially habitable planets scattered across the universe, the question arises, why have we yet to detect any signs of intelligent life? The paradox challenges our assumptions about life, intelligence, and the conditions necessary for their emergence. Given the billions of planets in the so-called Goldilocks zone, where conditions might support life, it seems logical to assume that intelligent life should be relatively common. However, the leap from simple single-celled organisms to advanced civilizations capable of technological progress may be much rarer than we expect. The history of Earth, filled with mass extinctions and environmental upheavals, further supports the argument that intelligent life might be fleeting. Our own species, for instance, has evolved through a series of catastrophic events, each of which has dramatically reshaped the course of life on our planet. This suggests that intelligent life, like ours, may be a temporary stage in the development of life as a whole, existing only for a brief moment in the grand timeline of the universe. Alternatively, the Fermi paradox may indicate that advanced civilizations do exist, but they choose not to communicate with us, or perhaps they communicate in ways that we are unable to detect. One possibility is that civilizations evolve to a point where their technological capabilities outstrip their ability to survive, ultimately leading to their self-destruction. In this scenario, the universe may be a vast graveyard of civilizations, each one rising to great heights, only to collapse before it can make contact with other life forms. Another possibility is that we are simply not looking for extraterrestrial signals in the right way. It is conceivable that our current technological tools and methods are insufficient for detecting signals from other civilizations, or that we are listening in the wrong frequencies or using incorrect methods. As our technology advances, new possibilities may emerge, sparking renewed efforts to search for our cosmic neighbors and challenging our existing assumptions about life beyond Earth. Planet 9, a hypothetical celestial body located at the far reaches of our solar system, has captured the imaginations of scientists and astronomers for years. Its existence is inferred primarily from the strange orbits of distant objects in the Kuiper Belt, a region of space beyond Neptune filled with icy bodies and remnants from the formation of the solar system. These peculiar orbits, exhibiting a clustering pattern, suggest the gravitational influence of a large, unseen planet. The characteristics of Planet 9, as it is called, are both intriguing and elusive. It is believed to be several times the mass of Earth, possibly 5 to 10 times larger, and its distance from the Sun could place it far beyond the orbit of Neptune, perhaps even hundreds or thousands of astronomical units away. If such a planet exists, it would be incredibly difficult to detect with current telescopes due to its vast distance and the faint light it would emit. Moreover, its orbit is thought to be highly elongated, taking tens of thousands of years to complete a single revolution around the Sun. Nevertheless, tantalizing evidence for Planet 9 comes from the unusual behavior of Kuiper Belt objects. Some of these objects appear to be influenced by the gravity of a massive, unseen planet, suggesting that they are being shepherded into similar orbits. This hypothesis has sparked ongoing research and debate, with scientists eagerly searching for any signs that might confirm the existence of this mysterious planet lurking in the distant corners of our solar system. The elliptical nature of celestial bodies, orbits, and their varied inclinations hint at a gravitational force that may be exerted by a mysterious and yet unseen entity, a massive planet hidden in the outer reaches of our solar system. While direct observations of this so-called Planet 9 have yet to be made, astronomers remain undeterred in their quest to find it. Armed with cutting-edge technology and the most advanced telescopes available, they continue to scan the heavens, hoping to spot any sign of this elusive world. The search for Planet 9 has become more than just a scientific endeavor. It has captured the collective imagination, stirring a sense of wonder about the hidden corners of the universe. As the search progresses, there remains an unwavering hope that this enigmatic planet will eventually reveal itself, expanding our understanding not only of our solar system, but of the broader cosmic landscape and the complex forces that govern it. The mystery surrounding Planet 9 also speaks to a larger truth about the universe. It is full of hidden wonders, many of which remain just out of reach. These discoveries, once made, could revolutionize our comprehension of space, and they continue to captivate both seasoned scientists and curious minds alike. Galaxies, too, come in all shapes and sizes, each one a unique story that unveils the intricacies of cosmic dynamics. Many galaxies appear irregular or distorted in shape, the result of gravitational interactions with nearby galaxies. These interactions can stretch and reshape galaxies, causing significant changes in their structures. When two galaxies pass near one another, their gravitational forces can pull at each other, causing their shapes to warp and even triggering the formation of new stars as gas clouds are compressed. Sometimes, spiral galaxies may become stretched out or take on new forms altogether. These gravitational interactions not only alter the physical structure of galaxies, but can also spark new areas of star formation, where clusters of new stars emerge from the compression of gas. In addition to these external forces, dark matter, an invisible and elusive substance that makes up a significant portion of the universe's mass, also plays a key role in shaping galaxies. While dark matter does not emit light or interact with electromagnetic radiation, it exerts a powerful gravitational pull that influences the structure of galaxies. Dense concentrations of dark matter can cause galaxies to take on peculiar shapes as they interact with the surrounding matter. Though we cannot see dark matter directly, its presence is felt throughout the universe, shaping not only the galaxies but also the larger structures that make up the cosmos. Furthermore, galaxies sometimes take on strange forms due to internal processes as well. Take, for example, starburst galaxies, which are experiencing an intense rate of star formation. In these galaxies, vast amounts of gas and dust coalesce, giving birth to new stars. The energy from these stars can propel gas and dust out of the galaxy in massive outflows or jets, which can lead to significant changes in the galaxy's overall shape. The continuous cycle of star formation combined with the violent forces of supernovae can carve galaxies into unexpected and dramatic forms. The environment in which galaxies exist also plays a crucial role in their evolution. In crowded galaxy clusters, galaxies may collide or merge, sometimes resulting in elliptical shapes as the two or more galaxies combine. The process of gas accretion, The gradual accumulation of gas into a galaxy can leave lasting marks on its shape. The gravitational pull of neighboring galaxies can further influence how a galaxy forms and evolves over time, imprinting unique features on its structure. In essence, the landscape of the cosmos is in a constant state of flux, with the shapes and structures of galaxies continuously evolving. These changes reflect not only the gravitational forces at play, but also the complex history of the universe itself. The stories told by galaxies are as old as the cosmos, and each one is a testament to the dynamic forces that govern the evolution of the universe. The idea of space tourism has evolved over the past few decades, shifting from a concept relegated to the realm of science fiction to a tangible possibility. It all began with the dream of space travel, and as technology advanced, that dream began to inch closer to reality. Companies like SpaceX and Blue Origin have made significant strides in rocket technology, propelling the vision of space tourism forward. Early ventures in space tourism primarily focused on suborbital flights, taking passengers just past the Kármán line, the internationally recognized boundary of space. These brief flights offered passengers a few minutes of weightlessness and the chance to gaze upon Earth from the vast expanse of space. As we look to the present day, the landscape of space tourism is rapidly changing. Private companies are pushing the boundaries of what is possible, and space travel is becoming more accessible than ever before. Blue Origin has successfully launched its New Shepard rocket, carrying private civilians on short journeys to experience the excitement of space firsthand. Meanwhile, SpaceX is continuing to refine its Crew Dragon spacecraft, designed not only to ferry private passengers into space, but also to transport astronauts to the International Space Station. As the cost of space travel gradually decreases thanks to advancements in technology, what was once the stuff of dreams is now on the verge of becoming a reality for an increasing number of people. Looking ahead, the future of space tourism is full of exciting possibilities. Companies are already exploring the idea of longer stays in orbit, with plans for commercial space stations where tourists can experience life in a microgravity environment for extended periods. There are even more ambitious plans for lunar tourism, including sending private passengers on trips around the moon, or even landing them on its surface. As technology continues to evolve and regulations adapt, the day may soon come when space tourism becomes as routine as air travel is today. The allure of space, once a far-off dream, is now closer than ever. However, the path to widespread space tourism is not without its challenges. The most pressing concerns revolve around safety, environmental impact, and cost. Ensuring the safety of passengers and crew is paramount, and advancements in safety protocols will be crucial in making space travel a routine and reliable activity. At the same time, the environmental footprint of space tourism will need to be carefully considered, as the increased number of launches could have significant implications for our planet. Finally, the cost of space travel must continue to decrease for it to become accessible to a broader range of people. If these challenges can be addressed, the dream of space tourism could one day become a commonplace reality, opening the final frontier to all who seek to explore it. As the warming of Earth's atmosphere and the growing accumulation of space debris continue to pose significant challenges, new advancements in space exploration are rapidly emerging. What was once considered a distant dream, the possibility of routine space travel, is increasingly becoming a reality. This new frontier in human exploration promises to unlock remarkable opportunities for scientific advancement and discovery, but it also brings with it a range of complex ethical concerns that cannot be ignored. One of the most pressing issues in space exploration today revolves around the potential impact on celestial bodies. As private companies venture further into the cosmos, questions arise. How can we ensure that we do not irreparably damage the environments of other planets and moons? The risk of contamination looms large, particularly when considering the possibility of Earth-based microbes contaminating potential alien ecosystems. Such an event could severely hinder astrobiological research and compromise the integrity of extraterrestrial environments. The protection of these environments is not only a matter of scientific importance, but also one of profound ethical responsibility. Another issue of growing concern is the commercialization of space. With private companies increasingly eyeing the moon, asteroids, and other celestial bodies as potential sources of resources, ethical dilemmas are emerging. The prospect of mining asteroids or extracting valuable materials from the moon raises fundamental questions about ownership and rights. Under current international space law, no nation can lay claim to celestial territories. However, as commercial interests grow, so does the risk of exploiting these resources without collaborative frameworks. Without careful regulation, we could be on the brink of a space gold rush, where profit-driven motives overshadow the imperative of responsible stewardship of our solar system. At the heart of these ethical debates lies the question of fairness. As space missions become increasingly privatized, access to the benefits of space exploration could become restricted to a small group of wealthy nations and private organizations. This raises significant concerns about equity and inclusivity. Space exploration has the potential to yield discoveries that benefit all of humanity. Yet, if only a select few are allowed to reap the rewards, the risk of exacerbating existing inequalities here on Earth is very real. The distribution of knowledge, resources, and opportunities derived from space research must be equitable, ensuring that all of humanity can share in the benefits of our expanding understanding of the cosmos. Furthermore, as we venture deeper into space, we are forced to confront larger existential questions about humanity's role in the universe. What responsibilities do we have, not just as stewards of Earth, but also as potential stewards of other worlds? The potential for colonization introduces a range of ethical dilemmas, particularly in regard to any indigenous life forms or sentient beings that may exist on other planets. As we explore these uncharted territories, it will be essential to engage in thoughtful dialogue about how we navigate these complex issues. Our actions in space must be guided by a commitment to sustainability and respect for the autonomy of any life forms that may already inhabit these distant worlds. In addition to the scientific and ethical implications, space exploration has had a profound impact on human culture, art, and literature. The discoveries we make in space ignite our imagination, inspire new forms of expression, and shape our cultural narratives. From ancient civilizations that crafted myths around celestial bodies to contemporary artists who explore the vastness of space in their work, the cosmos has always been a source of fascination. As our understanding of the universe deepens, so too does its influence on how we perceive ourselves and our place in the grand scheme of existence. Throughout history, artists have drawn on the concept of the universe to inspire their creations, whether through striking visuals that interpret the cosmic elements or through abstract representations that evoke feelings of infinity and mystery. The cosmos has provided a wellspring of creative inspiration. Artists like Vincent van Gogh, for example, captured the swirling night sky in ways that suggested not only movement, but also emotion, inviting viewers to contemplate their relationship with the vast, seemingly infinite cosmos. His work reminds us that the universe is not just a distant scientific concept, but a source of deep emotional connection and artistic expression. As we continue to push the boundaries of space exploration, we must carefully consider the ethical implications of our actions and the impact they will have on both our planet and the universe at large. The discoveries we make in space will undoubtedly shape the future of humanity. But how we choose to approach this new frontier will determine whether we chart a course toward a sustainable and equitable future, or one marked by exploitation and inequality. The journey ahead will require thoughtful collaboration, careful regulation, and a deep respect for the cosmic environments we seek to explore. Only through this approach can we ensure that the benefits of space exploration are shared by all, and that our legacy in the cosmos is one of responsibility, respect, and wonder. Contemporary artists frequently draw upon the vastness of outer space to reflect on the ethereal and the unknown. Through digital media, installations, and other innovative forms, they merge technology with imagination, bringing distant galaxies and cosmic phenomena into our everyday existence. These artistic explorations offer a glimpse into the infinite, inviting audiences to experience the beauty and mystery of space, often blurring the lines between the familiar and the surreal. The integration of space into art is not merely a trend, but a profound reflection on humanity's quest to understand the universe. to grapple with what lies beyond our reach, and to reimagine our place in the cosmos. In a similar vein, literature has been deeply influenced by space exploration, with authors turning to the stars as both a source of inspiration and a metaphor for the unknown. Space represents the ultimate frontier, an expanse that beckons with endless possibilities for discovery. Writers like Arthur C. Clarke and Isaac Asimov, pioneers in the genre of science fiction, have long used the vastness of space as a backdrop for stories that address technological advancements, societal evolution, and the ethical dilemmas posed by human expansion into the universe. Their works are not just tales of adventure, but intellectual explorations that reflect the rapid growth of astronomy, physics, and space science, while also probing the philosophical questions that arise from humanity's desire to reach beyond Earth. These narratives provoke a deeper contemplation of our future as a species. What will happen when we step beyond our planet's atmosphere? What responsibilities will we bear as we encounter new forms of life and explore new worlds? How will our interaction with the cosmos reshape our understanding of what it means to be human? In this way, literature and art do more than entertain. They challenge our perceptions, forcing us to confront the moral and existential questions that come with technological and exploratory advancements. This mutual relationship between space exploration and human culture forms an ongoing dialogue, bridging the gap between what we know and what we imagine. As science unravels the mysteries of the universe, these discoveries prompt both wonder and reflection. Art and literature become conduits for that reflection, not only celebrating our achievements, but also urging us to think deeply about the impact of our actions on the world and the cosmos. Through this continuous exchange, our understanding of the universe expands, and so does our understanding of ourselves. The discovery of alien life, whether microbial or intelligent, would be one of the most transformative moments in human history. Such a discovery would shake the very foundations of our understanding of life, identity, and our place in the universe. The realization that we are not alone in the cosmos would alter the trajectory of human civilization. It could foster a sense of unity across Earth's nations, transcending national borders and political ideologies, as we would collectively face the monumental implications of this discovery. This shared experience could potentially drive humanity toward collaboration, focusing on the preservation of life on Earth and the peaceful exploration of space. Moreover, the revelation of extraterrestrial life would prompt a reevaluation of international space laws and treaties. Currently, the Outer Space Treaty governs how nations interact with celestial bodies, but the discovery of alien life would raise new questions. Would we need to create protocols for first contact? How would we address the rights of alien life forms? And who would hold the claim to the resources found in space? The emergence of intelligent life elsewhere could lead to the development of new legal frameworks that require nations to work together in a responsible and ethical manner. However, the news of intelligent extraterrestrial life would not come without its challenges. The potential for fear, distrust, and even conflict could arise. Governments might feel compelled to prepare for any eventuality, spurring an arms race in space defense technology. Some nations might seek to exploit extraterrestrial discoveries for political or economic gain, while others could advocate for peaceful engagement and diplomatic relations. At the same time, religious and philosophical debates would emerge, as belief systems are tested by the reality of life beyond Earth. These debates could lead to societal divisions or inspire the birth of new movements that reframe humanity's understanding of its place in the grand scheme of existence. The scientific community would likely experience a surge of interest, resources, and funding as the discovery of alien life prompts new research initiatives. New branches of study would emerge, focusing on the complexities of extraterrestrial biology, culture, and technology. This shift could foster a new generation of scientists, ethicists, and thinkers who would dedicate their careers to studying the cosmos and preparing humanity for its role in the interstellar community. In many ways, the discovery of alien life would unite us in the pursuit of knowledge, propelling us to expand our horizons, both figuratively and literally. Sending humans to Mars represents one of the most ambitious goals in the history of space exploration, fraught with challenges that test the limits of our technological and human capabilities. The sheer distance between Earth and Mars is formidable, with the average distance between the two planets being approximately 39 million kilometers. A round-trip mission could take anywhere from 2 to 3 years, posing serious challenges related to crew health and the sustainability of life support systems. During this time, astronauts would be exposed to deep space radiation and microgravity, both of which present serious risks to their physical well-being. Radiation exposure is one of the most concerning issues for any mission to Mars. Unlike Earth, which is shielded by a magnetic field and atmosphere, Mars offers little protection from cosmic radiation and solar particles. Prolonged exposure to this radiation increases the likelihood of cancer, cataracts, and other serious health issues. Scientists are actively working to develop radiation shielding technologies, as well as potential pharmaceutical solutions to mitigate these risks. However, creating effective and affordable countermeasures remains a significant challenge. Life support systems also present major hurdles. Astronauts will need a reliable and sustainable way to produce oxygen, recycle water, and grow food throughout their extended stay on Mars. While progress has been made in creating closed-loop systems on the International Space Station, replicating these systems on Mars is far more complex due to the planet's harsh environment. Innovative methods such as using Martian soil to cultivate food or recycling atmospheric resources are crucial to ensuring the crew's survival. Mental health and crew dynamics are additional, often overlooked challenges. A Mars mission would require astronauts to live and work together in isolation for long periods, possibly without direct communication with Earth. The psychological strain of such an extended journey, along with the stresses of living in confined conditions, could undermine the mission's success. It is critical to develop support systems and contingency plans to address these challenges, ensuring the well-being of the crew and the success of the mission. The hurdles posed by the distance, radiation, life support, and psychological factors are significant, yet they also represent opportunities for groundbreaking advancements in human resilience and ingenuity. These challenges push the boundaries of what we can achieve, paving the way for future exploration beyond Mars and into the broader cosmos. The challenges of sustaining human life in space go far beyond the physical constraints of distance. In the vacuum of space, resources such as air, water, and food must be carefully managed and replenished. Without access to Earth's resources, astronauts are dependent on life support systems that recycle and reclaim every vital element. Spacecraft like the International Space Station rely on advanced technologies to maintain air quality by converting carbon dioxide into oxygen, and plants play an essential role in these systems through the process of photosynthesis. Water recycling is another critical aspect of space life support. The water on board must be continuously filtered and recycled, with systems designed to reclaim moisture from the air and even recycle wastewater. This process ensures that no drop of water is wasted, as it is a finite resource in space. Food production has also shifted toward more sustainable methods, with experiments in hydroponics and aeroponics underway to grow fresh produce without soil. These innovative farming techniques not only provide essential nutrients, but also offer psychological benefits, giving astronauts a sense of connection to Earth. Microgravity is another challenge for human health in space. The absence of gravity causes muscle atrophy and bone density loss, both of which must be addressed to ensure astronauts' physical well-being. Countermeasures such as exercise regimens and nutritional supplements are essential to maintaining health during long-duration missions. As research into these biological impacts advances, we are paving the way for longer missions and potential habitation on other celestial bodies. In our pursuit of the stars, innovative technologies continue to emerge that will make deep space missions more feasible. The development of advanced propulsion systems is one of the most promising areas of progress. Traditional rockets require massive amounts of fuel, limiting how far we can travel. However, new propulsion technologies could dramatically reduce the time and cost required to reach distant planets and moons, unlocking the potential for human exploration of the far reaches of our solar system and beyond. As we continue to push the boundaries of space exploration, we take one step closer to unraveling the mysteries of the universe and discovering our place within it. However, Emerging technologies like ion propulsion and nuclear thermal propulsion are reshaping the future of space travel, offering a glimpse into a new era of efficiency and rapid exploration. Ion propulsion works by generating thrust through the acceleration of ions, a process that allows spacecraft to travel for extended periods with significantly less fuel. This innovation not only enhances mission longevity, but also makes interplanetary journeys more sustainable. Unlike traditional chemical rockets, ion propulsion systems require far less fuel, enabling spacecraft to conserve resources and travel greater distances with minimal weight. Nuclear thermal propulsion, on the other hand, utilizes nuclear reactions to generate immense amounts of heat, which can be used to propel spacecraft. This technology has the potential to accelerate missions to distant planets and moons, drastically cutting down travel times and making space exploration more feasible. Whether it's journeying to Mars or venturing further into the outer solar system, nuclear thermal propulsion could be the key to unlocking faster and more efficient travel beyond Earth's orbit. Another remarkable frontier in space exploration is the development of life support systems that can sustain astronauts during extended missions, sometimes lasting for years. As missions stretch over prolonged periods, the need for self-sufficiency becomes increasingly crucial. Engineers are designing advanced systems capable of recycling air and water, ensuring a steady supply of essentials even in the most isolated environments. Closed-loop life support systems use cutting-edge filtering technologies and biological processes to maintain a breathable atmosphere and clean water, mimicking the life-sustaining cycles of Earth. This innovation reduces the need to transport vast quantities of supplies from Earth, making long-term space missions more practical and sustainable. More importantly, these systems contribute to the overall safety and well-being of astronauts, allowing them to thrive in the unforgiving conditions of deep space. Robotic technologies are also undergoing a revolution, enabling autonomous machines to assist with planetary exploration. These robots are being equipped with artificial intelligence that allows them to make decisions and solve problems based on real-time data. This level of autonomy is especially important for missions to distant worlds, where communication delays could prevent human intervention. With AI-driven drones and rovers, we can explore planets like Mars and the icy moons of Jupiter and Saturn without the need for constant human presence. These autonomous machines are capable of gathering valuable scientific data, sending it back to Earth for analysis, and even performing tasks that would be too risky for humans to undertake. As space missions venture farther into the cosmos, communication technology has evolved to keep pace. The challenges of transmitting data across vast distances are being met with the development of new generations of antennas and networks designed for laser communications. Unlike traditional radio waves, laser beams offer significantly higher bandwidth, making it possible to transmit large amounts of data much faster. This breakthrough enables scientists to receive information from distant missions in near real time, allowing them to analyze discoveries and make adjustments swiftly. The improvements in communication technology are fundamental for the success of deep space missions, ensuring that astronauts and robotic explorers remain in constant contact with Earth. Yet, as humanity pushes deeper into space, a growing concern looms over the presence of space debris. This debris, which consists of defunct satellites, spent rocket stages, and fragments from past collisions or missions, poses a serious threat to operational spacecraft and the International Space Station. Even small pieces of debris traveling at high velocities can cause catastrophic damage to critical infrastructure. As the number of satellites and spacecraft in orbit continues to rise, addressing the issue of space debris becomes increasingly urgent. One of the primary strategies for managing space debris is tracking. Scientists use ground-based radar and telescopes to monitor objects in orbit, creating comprehensive databases to identify potential collision risks. Agencies like the United States Space Surveillance Network maintain detailed records of thousands of debris pieces, which allows space agencies and satellite operators to make informed decisions regarding orbital adjustments. If a collision is imminent, these proactive measures enable spacecraft to maneuver out of harm's way, reducing the risk of accidents. To further mitigate the dangers posed by space debris, engineers are developing a range of innovative debris removal technologies. Concepts like nets, harpoons, and robotic arms are being tested to capture and deorbit larger pieces of space junk. The European Space Agency's Clear Space One mission, for example, aims to actively remove defunct satellites from orbit, reducing the likelihood of further debris creation. These groundbreaking solutions reflect a growing awareness of the need not only to track space debris, but to take direct action in cleaning up our orbital environment. In addition to active debris removal, there is also an increasing emphasis on designing spacecraft and satellites with debris reduction in mind. New guidelines and engineering practices focus on minimizing the creation of space debris during the design and launch of missions. By adopting these best practices, space agencies are working to ensure that future missions are conducted responsibly, reducing the environmental impact of human activity in space. These efforts are essential for maintaining the sustainability of space exploration, ensuring that future generations of astronauts and explorers will have a safe and clean environment in which to work. The sun, a relentless source of energy, plays a fundamental role in shaping life on Earth. Through the process of nuclear fusion, the sun generates an enormous amount of heat and light, driving the planet's weather patterns, ocean currents, and atmospheric systems. This radiant energy sustains life on Earth, creating the necessary conditions for ecosystems to thrive. The sun's influence is so powerful that it dictates the very cycles of life on our planet. One of the most significant ways the sun affects Earth's climate is through its radiation. Sunlight warms the planet, influencing air temperature, moisture levels, and atmospheric conditions. The distribution of solar energy across the Earth's surface creates varying climates in different regions. From the scorching deserts to the lush rainforests, each environment is shaped by the amount of solar energy it receives. This diversity in climates supports a wide array of ecosystems, each with its unique species of plants and animals, all adapted to their specific environment. Moreover, the sun's influence extends beyond climate to the rhythms of life itself. The cycle of day and night, determined by Earth's rotation, signals to living organisms when to be active and when to rest. This natural cycle regulates the biological processes of countless species, from the blooming of flowers to the sleep patterns of animals. Without the sun's energy, Earth would be a lifeless, frozen world, and the intricate dance of life that sustains us would cease to exist. Through this complex and dynamic relationship with the sun, life on Earth continues to thrive, a testament to the extraordinary power of our closest star. The changing seasons, driven by the tilt of Earth's axis as it orbits the sun, deeply influence the cycles of life across the planet. These seasonal shifts are not just a matter of temperature changes. They serve as key cues for the reproductive cycles, migration patterns, and growth phases of many species in nature. For example, plants and animals are intricately attuned to the rhythms of the sun, using its light as a guide to time their most crucial behaviors, from breeding to feeding. The sun's energy does far more than sustain life. It orchestrates the complex web of interactions between climate and ecosystems, fundamentally shaping the course of life on Earth. As we delve deeper into the study of solar influences, we are gaining a richer understanding of how even subtle variations in solar activity, such as solar flares or fluctuations in the sunspot cycle, can trigger far-reaching consequences for weather patterns, climate conditions, and ecological interactions. The sun is not just a distant source of warmth, it is the central architect of life itself, reminding us of the interconnectedness of all living things within our solar system. Similarly, supernovae, the explosive deaths of massive stars, play a pivotal role in the cosmic cycle of element creation and distribution. When these stars reach the end of their lifespans, they expel vast amounts of material at extraordinary speeds, releasing an array of elements into space. Many of these elements, including carbon, oxygen, and nitrogen, are fundamental for life as we know it. Without the cataclysmic event of a supernova, these essential building blocks would remain trapped within stars, unable to enrich the interstellar medium where planets are born. As the supernova detonates, it releases energy capable of igniting nearby clouds of gas and dust, triggering the formation of new stars and planetary systems. This process not only enriches the surrounding cosmic material with the heavy elements forged during the star's lifetime, but it also sets the stage for the birth of future generations of stars and planets. Each supernova, in essence, contributes to the chemical diversity of the galaxy, illustrating a profound cycle of creation and destruction. It is a cosmic cycle that nurtures the universe, setting the stage for the next chapter in the story of the cosmos. Moreover, the elements formed in these stellar furnaces, elements that are expelled during a supernova event, are vital for the creation of complex organic molecules. When new stars and planets form from the remnants of a supernova, they inherit these critical building blocks. Over time, these elements accumulate on planets, creating the conditions necessary for the chemical reactions that form life. This emphasizes the idea that the very material of our bodies, the elements that constitute life itself, were born in stars long before they ever came together to form our world as we know it today. In a broader sense, understanding the role of supernovae in dispersing essential elements allows us to better appreciate not just the formation of planets and life on Earth, but also the ongoing evolution of the universe itself. Each supernova represents a chapter in the grand cycle of stellar life, serving as a reminder that, in many ways, we are all made of star stuff, connecting our existence with the stars that once burned brightly long before our time. Cosmic events hold immense power over the conditions of life on Earth, influencing its environment in ways that range from subtle to dramatic. Our planet is constantly bombarded by cosmic forces, including solar flares, cosmic rays, and even the gravitational pull of distant celestial bodies. These influences are crucial in maintaining Earth's atmosphere and climate, which in turn support life. One of the most significant impacts comes from solar flares, violent bursts of radiation released by the sun. When directed toward Earth, these flares can disrupt satellite communications, cause power outages, and even alter climate patterns. Cosmic rays, high-energy particles from outer space, are another constant presence, bombarding our atmosphere. While they can pose risks to astronauts in space, on Earth they contribute to cloud formation and weather systems, showcasing how space weather is intertwined with life on our planet. Asteroid impacts represent another dramatic example of cosmic events shaping Earth's history. Though the chances of a catastrophic impact are low on any given day, the history of our planet shows that such events have had far-reaching consequences. Around 65 million years ago, a massive asteroid collided with Earth, contributing to the extinction of the dinosaurs. This cataclysmic event not only altered the planet's climate, but also opened the door for mammals to thrive, eventually leading to the evolution of humankind. The long-term future of Earth may also be influenced by other cosmic phenomena, such as supernova or gamma-ray bursts. These explosive events can release vast amounts of energy, potentially damaging the ozone layer and raising radiation levels on Earth. As we continue to deepen our understanding of these cosmic processes, it becomes clear that the universe is not a distant observer of life on Earth. It is actively shaping our planet's biological destiny. This highlights the profound connection between Earth and the cosmos, a reminder that we are part of a much larger, interconnected universe. Private companies are increasingly playing a crucial role in the expanding field of space exploration. While space travel has historically been dominated by government agencies, in recent years, private enterprises have made significant strides, transforming the landscape of space missions. With breakthroughs in technology and substantial investments, companies like SpaceX, Blue Origin, and Virgin Galactic are not only pushing the boundaries of space travel, but also reshaping the economics of these missions. A key innovation from the private sector is the development of reusable rocket technology. SpaceX, for instance, has pioneered a system in which rockets can return to Earth after launching their payload and land safely for reuse. This innovation has drastically lowered the costs of space access, making it more affordable than ever before. As private companies continue to refine these technologies, they are paving the way for a new era of space exploration. This includes more frequent and diverse missions, such as satellite deployment, space tourism, and the eventual prospect of manned missions to Mars. The increasing involvement of private sector players promises to accelerate humanity's reach beyond Earth, opening up new frontiers of discovery and exploration in the vast expanse of space. Moreover, private companies are rapidly expanding the commercial landscape of space, with growing interest in satellite internet services and asteroid mining. These entities are pioneering innovative business models that could ultimately shape the future of space economies. This shift is not only driving technological innovation, but also fostering collaborations between private companies and government agencies. Together, they are addressing the myriad challenges that space exploration presents. As we look to the future, the role of private companies will likely extend far beyond launching rockets. These companies are poised to play critical roles in areas such as space habitat development, lunar missions, and interplanetary exploration. With their entrepreneurial spirit and willingness to take risks, private entities are redefining the possibilities of space exploration, making it more inclusive and dynamic than ever before. As humanity sets its sights on the future of lunar exploration, scientists and engineers have begun drafting ambitious plans for lunar bases that could serve as hubs of activity on the moon. These outposts are envisioned as multifaceted facilities where astronauts and scientists could engage in a range of activities, from scientific research to resource extraction. The moon's proximity to Earth makes it an ideal location for establishing a permanent human presence. Such a presence would be crucial for facilitating deeper space exploration in the future. One of the primary purposes of these lunar bases will be scientific research. The moon offers a unique environment for studying celestial bodies, helping scientists understand the formation of our solar system and the early history of our planet. Researchers believe that lunar samples could reveal vital clues about the extreme conditions and processes that have shaped not only the moon, but also Earth itself. Furthermore, the moon's lack of atmosphere and light pollution offers an unparalleled opportunity for astronomical observations, opening doors to experiments that would be impossible on Earth. Lunar bases will also serve as crucial testing grounds for technologies needed for future missions to Mars and beyond. By establishing infrastructure such as habitats, life support systems, and energy generation capabilities on the moon, scientists and engineers can refine their designs in a relatively nearby environment. Learning to live and work on the moon will provide invaluable data, helping researchers overcome the challenges of sending humans further into the solar system. The moon's proximity allows for experimentation with systems that would be necessary for longer, more distant missions, acting as a proving ground for future exploration efforts. Moreover, lunar bases could pave the way for the utilization of resources in space. The moon is believed to harbor valuable resources, such as water ice, particularly in its polar regions. This water could be converted into oxygen and hydrogen, providing fuel for rockets. Such resource utilization would not only support lunar missions, but also make human exploration throughout the solar system more sustainable. By harnessing the moon's resources, we could reduce the need to launch all supplies from Earth, making space exploration more cost-effective and sustainable in the long term. These futuristic lunar bases hold the potential to not only expand our reach, but also deepen our understanding of the cosmos. The possibilities of lunar exploration are nothing short of thrilling, and the advancements in technology and infrastructure needed to make this vision a reality are progressing rapidly. One of the most exciting developments on the horizon is the concept of warp drive, a groundbreaking idea once confined to science fiction. This technology envisions a method of faster-than-light travel by manipulating space itself. Inspired by the theories of physicist Miguel Almaguer, warp drive seeks to achieve extraordinary speeds without violating the fundamental laws of physics, including Einstein's theory of relativity. The concept involves manipulating space by contracting it in front of a spacecraft while expanding it behind, creating a warp bubble that would allow the craft to travel through space-time at unprecedented speeds. While research into warp drive is still in its early theoretical stages, scientists and engineers are investigating the underlying physics. One of the greatest challenges is the enormous energy required to generate a warp bubble. Initial calculations suggested that the energy needed would be equivalent to the mass energy of entire planets. However, recent advancements in theoretical physics could offer new insights into how we might achieve more feasible energy solutions. Though there are no current experimental setups to directly test the concept, researchers at NASA's Eagle Works laboratory are investigating exotic materials and negative energy, which may be necessary to create and sustain a warp bubble. Their work, though largely theoretical, is laying the groundwork for future experiments that could one day make warp drive a reality. The potential for warp drive to revolutionize space travel remains uncertain, but its allure is undeniable. While we may be far from boarding a warp-capable spacecraft, ongoing research continues to fuel our curiosity and imagination about what lies beyond our solar system. The dream of interstellar travel through warp technology keeps pushing the boundaries of what we thought was possible, inspiring scientists to explore new frontiers of physics and space exploration. As space missions continue to evolve, robotics is playing an increasingly vital role in exploring the rugged and inhospitable surfaces of distant planets and moons. These robotic systems, such as rovers and landers, allow us to investigate locations that are too remote or dangerous for humans to visit directly. Equipped with a suite of scientific instruments, these robots can collect data, perform experiments, and send valuable information back to Earth. One of the most notable examples of robotic exploration is NASA's Perseverance rover, which is currently exploring the surface of Mars. This advanced rover is tasked with searching for signs of ancient life and collecting samples that may one day be returned to Earth. With its remarkable mobility and agility, Perseverance is able to traverse the Martian terrain, analyzing soil and rock compositions along the way. Its onboard laboratories provide researchers with critical data about the Martian environment, all without putting human lives at risk. The role of robotics is not limited to Mars. Robotic missions are also venturing to the icy moons of our solar system, such as Europa and Enceladus, where robotic landers may one day drill through frozen crusts to access subsurface oceans. These missions harness cutting-edge technology to explore environments that may harbor the building blocks of life. The possibility of discovering life in these distant extreme environments drives forward the search for extraterrestrial life in our solar system and beyond. Robotics offers us the chance to probe these remote and inhospitable worlds in ways that were once unthinkable, providing a deeper understanding of the vast, mysterious cosmos. As robotic technology advances, the future of planetary exploration becomes increasingly promising. Thanks to cutting-edge innovations in artificial intelligence, machines are now capable of making autonomous decisions, significantly enhancing their ability to navigate hazardous terrains and adapt to unexpected challenges. This evolution in technology ensures that robots will remain at the forefront of humanity's quest to uncover the mysteries of distant worlds. With each new advancement, they open pathways to discoveries we have yet to imagine, pushing the boundaries of exploration to new heights. In the realm of planetary science, astronomy and geology intersect in fascinating ways to unlock the secrets of planetary surfaces. These two disciplines work in tandem, revealing the complex histories and processes that have shaped celestial bodies, from planets and moons to the far reaches of the solar system. By applying geological principles to astronomical data, scientists can reconstruct the evolution of a planet's surface and assess its potential for harboring life, both in the past and present. Astronomers use powerful telescopes and spacecraft to gather critical data about the atmospheres, temperatures, and surface features of distant planets. This data is often complemented by geological studies of Earth, where scientists apply their extensive knowledge of rock formations, erosion, and volcanic activity to interpret extraterrestrial landscapes. For instance, when a spacecraft sends back high-resolution images of Mars, geologists can carefully analyze those images to identify ancient riverbeds or vast volcanic plains. These geological signatures provide invaluable clues about the planet's climatic history and its potential for past life. Moreover, planetary geology also draws on data from meteorites and lunar samples, which come from asteroids, comets, and other celestial bodies. By studying these materials, scientists can make comparisons between Earth and other planets, offering a more comprehensive understanding of the forces shaping planetary surfaces. This comparative approach has led to a deeper understanding of how different surfaces have evolved over time. For example, by studying the craters on the Moon, researchers can interpret similar features found on planets like Mercury or Mars, providing insights into the impact history of these worlds. Ultimately, the collaboration between astronomy and geology is crucial for advancing our understanding of the solar system. As technological advancements continue and missions to explore planets like Venus or the icy moons of Jupiter, such as Europa, become more frequent, the synergy between these two fields will only grow stronger. This partnership not only illuminates the history of our solar system, but also guides our search for life beyond Earth, as well as our understanding of planetary formation across the universe. In the realm of space exploration, computer science plays a pivotal role in processing astronomical data, allowing scientists to unlock the mysteries of the cosmos with unprecedented efficiency. Modern telescopes and observatories generate vast quantities of data about distant stars, galaxies, and celestial phenomena. Without computer algorithms and advanced software, this data would remain an overwhelming mass of raw information. Today, instruments are capable of generating petabytes of data, equivalent to millions of gigabytes, in a matter of hours. The sheer scale of this data demands powerful computational tools to process and analyze it effectively. One of the key contributions of computer science to astronomy lies in data storage and management. Astronomical observations produce massive data sets that need to be stored securely and accessed quickly for analysis. Specialized databases designed for astronomical data enable researchers to efficiently query and retrieve information. Cloud computing further enhances this capability, allowing teams from around the globe to collaborate in real time, regardless of their physical location, and to process data collectively. The analysis of astronomical data has also been transformed by advanced algorithms, many of which are inspired by artificial intelligence and machine learning. These algorithms sift through vast data sets to identify patterns, classify celestial objects, and even detect anomalies that could suggest new astronomical phenomena. Machine learning, for example, has proven highly effective in classifying supernovae from the complex light curves of distant stars. By automating this classification process, astronomers can focus their efforts on the most promising candidates, dramatically accelerating the pace of discovery. Moreover, the development of sophisticated visualization tools through computer science has made it easier for researchers to communicate their findings to both the scientific community and the public. Complex data can be transformed into engaging visual formats, such as interactive 3D models or informative graphs, making it more accessible and understandable. These visualizations not only enhance the comprehension of complex scientific concepts, but also spark curiosity about the universe, inspiring the next generation of explorers and researchers. Through its intricate connection to astronomy, computer science has become more than just a tool. It has become a critical partner in the exploration of the cosmos. It empowers scientists to analyze vast data sets, interpret celestial phenomena, and communicate their findings to the world in ways that were once unimaginable. Together, these disciplines are unlocking the deepest secrets of the universe and continuing to push the limits of human knowledge. The intersection of biology, chemistry, and space exploration presents another fascinating frontier, particularly in understanding how life can survive and adapt beyond Earth. As we venture deeper into space, scientists are focusing on the fundamental building blocks of life and the chemical processes that sustain it. This intersection becomes especially crucial when considering long-duration missions to distant planets, such as Mars, where the survival of astronauts depends on understanding both biological needs and chemical interactions in an extraterrestrial environment. Astrobiology, the study of life in the universe, plays a pivotal role in this area of research. Scientists are investigating the chemistry of extraterrestrial environments, searching for the elements and compounds necessary for life to thrive. By studying extreme conditions on Earth, such as the depths of the ocean or acidic lakes, researchers can draw parallels with potential habitats on other planets. This knowledge helps determine where we might find life beyond Earth and informs the development of technology and biological solutions necessary to sustain life in these alien environments. Life support systems essential for long-term space missions rely heavily on chemical processes to recycle air, water, and nutrients. Understanding these processes is vital for ensuring the health and well-being of astronauts during their voyages. For instance, the ability of plants to convert carbon dioxide into oxygen through photosynthesis is a crucial part of creating sustainable environments in space. The collaboration between biologists and chemists ensures that these life support systems are not only effective but also efficient, enabling astronauts to survive in the harsh conditions of space. Ultimately, the intersection of biology, chemistry, and space exploration is a multidisciplinary approach that will help pave the way for humanity's future in space. By deepening our understanding of life's fundamental processes, we can better prepare for the challenges of long-term space travel, ensuring that future generations of explorers can live and work comfortably beyond Earth. As we continue to push the boundaries of space exploration, this collaboration will be key to unlocking the potential for human life on other planets and ensuring the sustainability of our missions in the vastness of space. Experiments conducted aboard the International Space Station (ISS) vividly illustrate the deep synergy between space exploration and various scientific disciplines. Scientists have delved into the effects of microgravity on a range of biological processes, including the growth patterns of bacteria and plants. The unique chemical reactions that occur in space offer a rare window into fundamental biological and chemical principles that would otherwise remain hidden on Earth. Through these experiments, we continue to uncover the remarkable resilience of life itself, as well as the intricate, often unexpected interactions between biological and chemical systems. These discoveries are not just academic. They pave the way for future explorations further into the cosmos, guiding us toward a deeper understanding of life's adaptability and the mechanisms that allow it to flourish in even the most extreme environments. Engineering plays an indispensable role in driving innovations that are pushing the boundaries of space travel and exploration. At its core, engineering is about problem solving, and the challenges posed by sending both humans and machines beyond the confines of our planet require ingenuity and precision. Engineers harness their expertise to create solutions that make the impossible possible, from designing rockets and spacecraft to developing advanced life support systems. These innovations ensure that we can explore the far reaches of space with both safety and efficiency. Among the most profound breakthroughs in recent years is the development of reusable rocket technology. This groundbreaking advancement has dramatically lowered the cost of accessing space, making it more feasible to send missions into orbit with reduced financial burdens. Engineers at companies like SpaceX have pioneered designs that enable rockets to return to Earth after their missions, dramatically cutting costs and allowing for more frequent launches with the same hardware. This new paradigm is reshaping the way we think about space exploration, blending creativity with engineering expertise to enhance our capabilities and open new doors for both scientific exploration and commercial space ventures. Beyond rocket technology, advances in materials science have revolutionized space exploration in profound ways. Engineers have developed lighter, stronger materials that can withstand the extreme conditions of space, such as the searing heat of re-entry into Earth's atmosphere. Innovations like heat shields, capable of enduring temperatures that would vaporize ordinary materials, ensure that spacecraft can return safely to Earth after completing their missions. As the search for ever better materials continues, engineers focus on performance characteristics like insulation, structural integrity, and radiation shielding, all of which are essential for ensuring the survival of both equipment and human passengers in the harsh environment of space. This unrelenting drive to improve allows for the creation of spacecraft that can endure the unforgiving realities of space travel, pushing the boundaries of what's possible. In tandem with these material advancements, the integration of advanced technologies like artificial intelligence, AI, and robotics is reshaping the landscape of space exploration. Engineers are designing intelligent systems capable of operating autonomously in the vast emptiness of space. These systems include rovers that traverse alien terrains, satellites that adapt to changing conditions, and robots that can carry out complex tasks without direct human intervention. Such innovations do not just extend our exploration capabilities, they also deepen our understanding of the universe. As AI and robotics continue to evolve, our capacity to explore, comprehend, and ultimately inhabit the vast expanse of space grows ever greater, heralding new opportunities for discovery and insight. The discovery of the Higgs boson in 2012 marked a monumental milestone in the field of particle physics, reshaping our understanding of the fundamental structure of the universe. Often referred to as the God particle, the Higgs boson plays a crucial role in explaining how other particles acquire mass, an essential element of the standard model of particle physics. Before its discovery, the mechanism by which particles gained mass was one of the most perplexing mysteries in science. The Higgs boson is tied to the Higgs field, an invisible energy field that permeates the universe. As particles move through this field, they interact with it, and in doing so, gain mass. Without this process, fundamental particles like electrons and quarks would remain massless, and the universe as we know it would be an entirely different place. This breakthrough has profound implications, not only enhancing our understanding of atomic formation, but also shedding light on the very structure of matter itself. From the formation of stars to the creation of planets, and ultimately the emergence of life, the insights unlocked by the Higgs boson are reshaping the foundations of physics. Furthermore, the discovery of the Higgs boson has opened new avenues of research, leading scientists to explore the possibility of phenomena that lie beyond the current framework of the Standard Model. One of the most tantalizing prospects is the existence of dark matter, an enigmatic substance that makes up about 27% of the universe, yet remains largely invisible and undetectable. Understanding the Higgs boson could provide crucial insights into how dark matter interacts with ordinary matter, bringing us closer to solving one of the universe's most perplexing mysteries. As we continue to probe the nature of the Higgs boson and its associated field, it is clear that this discovery marks only the beginning of a new era in physics. It compels us to reconsider not only the building blocks of matter, but also the broader structure of reality itself, as we seek to understand the deep, interconnected fabric of the universe. With each discovery, we peel back layers of complexity, revealing a universe that is not just vast, but intricately woven together. Our journey into the cosmos continues to push the boundaries of knowledge, and each new breakthrough brings with it more questions, propelling us into uncharted territories of scientific inquiry. Space exploration in particular offers profound insights that challenge and expand our understanding of humanity's place in the cosmos. As we look beyond Earth, we are confronted with a universe that stretches endlessly in every direction, filled with countless stars, planets, and phenomena. This perspective can be humbling. It reminds us that Earth is but a small oasis in an immense cosmic ocean. When we gaze at the night sky, we might feel both a sense of isolation and an overwhelming sense of connection to a universe that has existed long before our species ever emerged. Moreover, the discovery of exoplanets, planets located beyond our solar system, has fundamentally altered our view of the potential for life beyond Earth. Thousands of these distant worlds have been identified, many of them located in the habitable zone of their stars, where conditions may be suitable for life to exist. The search for extraterrestrial intelligence, SETI, fuels our curiosity about life beyond Earth, sparking philosophical questions about our place in the cosmos. Are we truly alone, or is life emerging in various forms throughout the universe? These questions challenge the anthropocentric view that humans are the pinnacle of evolution, urging us to consider the possibility that life may exist in forms entirely different from our own, and perhaps even be capable of exploring the cosmos in ways we cannot yet comprehend. The findings of missions such as the Mars rovers and the Voyager spacecraft further enrich this conversation, offering tantalizing evidence that life could indeed exist beyond Earth. Mars, once thought to be a barren, lifeless planet, has revealed signs of ancient water, and some scientists speculate that microbial life may have once thrived there. This possibility reshapes the narrative of life's rarity in the universe, encouraging us to rethink the uniqueness of our existence. It also highlights the astounding adaptability of life, suggesting that it might find a way to thrive even in the harshest environments. These discoveries raise important questions about the potential for life elsewhere in the universe and expand our understanding of what life can be. Finally, the very act of exploration calls upon us to confront our responsibilities as stewards of our home planet. The more we learn about the vastness of the universe, the more we realize how fragile and precious Earth is in its capacity to support life. Our place in the cosmos carries with it a profound obligation to protect and preserve this unique planet. As we continue to expand our horizons through space exploration, we are reminded of both the fragility of our existence and our incredible potential to explore, understand, and safeguard the wonders of the universe.